Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient dance between human observation and cosmic visitors. A story that begins in the flickering lamplight of Babylon and ends with robotic eyes detecting objects from distant stars. A tale where the boundary between prediction and summoning grows mysteriously thin. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The night breathes slowly over the Mesopotamian plain, carrying the scent of irrigation channels carved deep into fertile soil, the distant whisper of date palm fronds stirring in warm winds that have blown across these lands since before written memory began. Above the great city of Babylon, that marvel of hanging gardens and towering walls, the sky spreads like black silk pierced by countless silver needles, each star a mystery waiting to be decoded by patient human eyes. The air itself holds weight here, thick with the humidity of the Euphrates and Tigris rivers, those twin arteries that have nourished civilization since humanity first learned to scratch marks into clay tablets. Tonight, that same humid air creates remarkable atmospheric stability, reducing the twinkling that normally obscures stellar observations. The priests understand this phenomenon without naming it, choosing moonless nights with still air for their most delicate measurements. The year drifts somewhere between 750 and 650 BCE, though time itself moves differently in this era before mechanical clocks, measured instead by the slow wheel of seasons and the patient cycles of celestial wanderers. The Neo-Babylonian Empire reaches toward its zenith under kings whose names will thunder through history: Nebuchadnezzar II, builder of impossible gardens, Nabonidus, the scholar king who spends more time studying ancient tablets than governing his realm. These rulers understand intuitively that knowledge of heaven translates to power on earth, that the ability to predict eclipses and planetary conjunctions grants legitimacy to royal dynasties. But tonight, high atop the seven-tiered ziggurat dedicated to Marduk, that ancient god of order who brought cosmos from chaos, the priest astronomers pursue something more fundamental than political advantage. They pursue truth written in light. Patterns hidden in the dance of worlds, secrets that whisper across the void between stars. Nabu Rimani adjusts his position on the temple's highest platform, 7 stories above the sleeping city. Clay tablet balanced carefully on his knees like a precious offering, his weathered hands, stained with the ink of crushed charcoal and gum arabic, grip a bronze stylus worn smooth by decades of use. The instrument feels warm from his palm, familiar as a craftsman's favorite tool. His name will survive 27 centuries into the future, carved on cuneiform tablets that modern archaeologists will discover in the ruins of ancient libraries. His observations so precise that contemporary astronomers will wonder if he possessed some form of primitive telescope. Tonight, though, he simply watches. His eyes, trained through 40 years of systematic observation, track a particular star that moves. One member of that celestial flock the Babylonians call Bibu, the wild sheep. The term carries poetry that later astronomical language will lose. These bright points truly do seem like luminous animals grazing across an endless dark pasture, following invisible paths known only to themselves. The observation platform spreads around him like a carefully designed instrument. Carved stone markers indicate the precise positions of rising and setting stars at different seasons. Bronze gnomon posts cast shadows that divide the night into measured intervals. Shallow basins filled with still oil serve as primitive artificial horizons, their mirror-dark surfaces reflecting star positions for more accurate measurements. The entire ziggurat functions as an enormous astronomical instrument, its orientation calculated to align with significant stellar events. Venus rises before dawn, brilliant white fire burning through the atmospheric haze above the eastern horizon. She climbs steadily higher, outshining every other celestial object save the sun and moon themselves. The priests know her by two names: Ishtar of the morning, radiant herald of sunrise; Ishtar of the evening, silver lamp hanging in the western twilight. They have not yet realized that morning star and evening star share a single identity. That discovery will wait for Greek geometers still centuries in the future. The goddess star follows cycles within cycles, patterns that repeat with mathematical precision, yet never exactly the same. Every 584 days, she returns to the same position relative to the sun, but her altitude and brightness vary subtly. Sometimes her morning appearances last longer, sometimes shorter. Sometimes she climbs high into the zodiac, sometimes she hugs close to the horizon. The priests track these variations with religious devotion, sensing deeper mysteries hidden within the apparent repetition. What they cannot know, cannot possibly comprehend from their earthbound perspective, is that they map gravitational architecture spanning millions of miles. Every careful measurement of Venus's synodic period describes part of an invisible structure through which objects travel between worlds. The mathematics they develop to predict her disappearances behind the sun's glare will one day guide spacecraft through the outer solar system. The geometric principles they discover by watching her trace elegant loops across the zodiac will inform computer algorithms designed to detect the hyperbolic trajectories of interstellar visitors. Mars presents an even greater puzzle. The Red Wanderer moves forward through the zodiac for months at a time, then suddenly stops, reverses direction, loops backward through the star patterns, stops again, and resumes his forward journey. This retrograde motion defies simple explanation. The planet seems to follow no consistent rule, sometimes completing small loops, sometimes large ones, sometimes spending weeks in retrograde, sometimes months. Nabu Rimani has devoted half his lifetime to understanding Mars. His tablets contain hundreds of observations spanning decades, positions measured against background stars, brightness variations carefully noted. The complex timing of each retrograde loop precisely recorded. Slowly, very slowly, a deeper pattern emerges. The loops are not random. They repeat, not in simple cycles, but in vast spiraling rhythms that span multiple decades. The work requires extraordinary patience. A single complete observation of Mars, tracking him through all his phases from one opposition to the next, takes more than 2 years. Understanding his retrograde behavior demands tracking multiple oppositions, watching the loops shift slowly against the stellar background. Saturn moves so slowly through the zodiac that mapping his complete orbit requires multiple generations of observers. Knowledge passed from master to student like a sacred flame burning continuously across centuries. The priests develop elaborate systems of notation. They create standardized symbols for planetary positions, mathematical techniques for interpolating between observations, methods for predicting future locations based on past patterns. They invent the first coordinate grids overlaid onto the celestial sphere, dividing the sky into manageable sections that can be systematically monitored and recorded. In the pre-dawn hours, when Babylon sleeps and only the temple fires burn with steady light, something profound begins to happen. The accumulated weight of generations starts to reveal hidden architecture, not merely the individual movements of planetary wanderers, but the deeper mathematical structure underlying all celestial motion. The priests cannot name gravitational force or describe elliptical orbits in modern terminology, yet their measurements capture these phenomena with startling precision. Kidinu, the astronomer, working 3 centuries after Nabu Rimani inherits tablets containing thousands of observations. He develops mathematical models of unprecedented sophistication, algorithms that predict lunar eclipses decades in advance with accuracy that will not be matched until the invention of mechanical computers. His calculations incorporate subtle knowledge of the Moon's slightly elliptical orbit, the variations in her speed as she travels through different portions of her path around Earth. The mystery deepens when modern scholars examine these ancient predictions. Kidinu's eclipse calculations differ from modern computer models by mere minutes, precision that seems impossible for naked-eye observations made without telescopes or mechanical clocks. Either the Babylonian astronomers possessed extraordinary observational abilities, or they had access to information sources that remain mysterious even today. The great astronomical schools of Babylon begin producing ephemeris tables by 400 BCE, detailed predictions of planetary positions extending centuries into the future. These documents, inscribed on hundreds of clay tablets using cuneiform script that encodes complex mathematical relationships, represent humanity's first successful attempt to peer forward through time using predictive models. The same conceptual breakthrough that enables modern computers to calculate when and where interstellar objects might appear in our skies. The tablets reveal something else remarkable. The Babylonian astronomers don't simply record what they observe. They develop confidence that the universe operates according to discoverable laws. They assume that celestial mechanics will continue following the same patterns they have detected through careful observation. This represents a profound philosophical leap, from passive recording to active prediction, from observing the past to calculating the future. The priests establish observational protocols that echo through millennia. They develop standardized methods for measuring star positions using the human body as a reference frame. A fingertip held at arm's length subtends approximately 1 degree of arc. They create techniques for tracking moving objects against the background of fixed stars, systems for recording and sharing astronomical data across vast distances and long periods of time. They build the first star catalogs, mapping stellar positions with accuracy that will not be improved until the invention of the telescope. Perhaps most remarkably, they begin to understand that observation itself possesses a kind of creative power. By watching the sky systematically, by developing mathematical methods to predict celestial events, they participate in cosmic unfolding rather than merely witnessing it. Their calculations don't simply describe planetary movements, they seem to call those movements into mathematical existence. The same mysterious relationship between observation and manifestation that will perplex quantum physicists 25 centuries later. The ziggurat never sleeps. Day and night, throughout all seasons, trained observers maintain their vigil. They track the slow precession of equinoxes, the shifting relationship between stellar backgrounds and seasonal markers. They map the zodiacal band through which planets wander, dividing it into 12 sections that provide a coordinate system future astronomers will recognize and refine. They develop increasingly sophisticated instruments, bronze astrolabes for measuring star altitudes, elaborate shadow clocks for timing observations, water clocks that mark the passage of hours with steady precision. Knowledge accumulates like fertile silt deposited by annual floods, layer upon layer of careful measurement building toward deeper understanding. The priests train their successors in observation techniques passed down through generations. They establish schools where students learn to read both the night sky and the accumulated wisdom inscribed on thousands of tablets stored in temple libraries. They create the first astronomical databases, organized collections of celestial observations that can be searched and analyzed for hidden patterns. They cannot imagine that their patient work establishes the conceptual foundation for robotic sky surveys. The same principles of systematic observation, pattern recognition, and predictive modeling that guide their studies will eventually power automated telescopes scanning for objects from distant stars. The same dedication to watching waiting, and recording will be encoded into computer programs capable of monitoring millions of celestial objects simultaneously, detecting anomalies that human eyes could never notice. The stars wheel overhead in their eternal dance, carrying secrets that only the most patient observers might decipher. Venus fades into the growing light of dawn, her morning apparition nearly complete. Soon she will disappear behind the sun's glare for 8 days before emerging as evening star in the western sky. The priests already know this, have calculated the timing centuries in advance. Their predictions inscribed on tablets that future archaeologists will marvel at for their precision. Nabu Rimani presses the final cuneiform marks into his tablet, adding another night's observations to humanity's first systematic database of celestial motion. Somewhere in that accumulated knowledge, in those thousands of careful measurements tracking planetary wanderings across the zodiac, lie the mathematical pathways through which visitors from distant stars might one day travel toward our small blue world. The mystery waits, patient as stone, hidden in patterns that human minds are only beginning to comprehend. The Mediterranean sun climbs toward its zenith, casting sharp shadows across the marble colonnade of the Library of Alexandria. Here, where the Nile Delta spreads its fertile fingers toward the sea, human understanding of celestial mechanics takes its next profound leap forward. The year hovers near 150 BCE, and within these halls lined with papyrus scrolls, Greek geometers apply mathematical precision to the patient observations inherited from Babylon. Hipparchus of Nicaea sits cross-legged on a woven mat, bronze compass in one hand, a reed pen in the other. Before him spreads a sheet of papyrus covered with circles, triangles, and arcs, the geometric language through which he translates planetary motion into pure mathematics. The Babylonian clay tablets rest nearby, their cuneiform records of Venus and Mars transformed now into Greek numerical notation, ready to yield their deeper secrets to geometric analysis. The Greeks possessed something the Babylonians lacked, an obsession with geometric proof, where the earlier astronomers were content to discover patterns and make predictions. Hipparchus demands to understand why the patterns exist. He seeks not merely to predict when Venus will appear as morning star, but to construct a geometric model that explains her complex motion through three-dimensional space. His breakthrough comes through patient triangulation. By measuring the precise angles between stars at different times of night, he can calculate stellar distances with unprecedented accuracy. The technique requires observations separated by months or years, as Earth's orbital motion provides the necessary baseline for triangulation measurements. What he discovers revolutionizes human understanding of cosmic scale. The nearest stars lie impossibly far away, so distant that even Earth's orbital diameter appears as a mere point when viewed from stellar distances. This realization carries profound implications. If the stars show no parallax shift as Earth orbits the Sun, they must be separated from our solar system by gulfs of space that dwarf anything previously imagined. The universe suddenly becomes vast beyond comprehension, filled with distances that human minds can calculate but barely grasp. Hipparchus develops trigonometric tables that will survive for 2 millennia, mathematical tools so precise that medieval Islamic astronomers will copy them unchanged. His calculations of lunar distance differ from modern measurements by less than 1%, remarkable accuracy achieved using nothing more sophisticated than careful angular measurements and geometric reasoning. The same triangulation principles that guide his work will eventually enable spacecraft to navigate between planets with extraordinary precision. Yet perhaps his most mysterious accomplishment involves the discovery of precession. By comparing his own star positions with those recorded by earlier astronomers, Hipparchus detects an almost imperceptible shift in the stellar coordinate system. The entire celestial sphere appears to be rotating slowly, completing one full revolution every 26,000 years. This phenomenon, the wobbling of Earth's rotational axis, will not be fully explained until Newton develops his theory of universal gravitation 18 centuries later. The precession discovery reveals something profound about the relationship between observation and time. Hipparchus realizes that truly accurate astronomy requires observations spanning multiple human generations. Individual lifetimes are too brief to detect the most fundamental celestial cycles. Only by building upon the work of predecessors, only through institutional memory preserved in written records, can human understanding penetrate the deepest rhythms of cosmic motion. In the great halls of the library, scholars from across the Mediterranean world gather to share astronomical knowledge. Apollonius of Perga contributes his theory of epicycles, circles moving along circles, which provides the first geometric explanation for planetary retrograde motion. Aristarchus of Samos proposes that Earth orbits the Sun rather than vice versa, a revolutionary idea supported by geometric reasoning, but rejected because it conflicts with common sense observation. The Greeks developed the astrolabe, that elegant bronze computer which encodes the entire celestial sphere on a flat metal disk. With skilled manipulation, the instrument can predict star positions, calculate sunrise and sunset times, determine the date from stellar observations, and solve dozens of other astronomical problems. The astrolabe represents humanity's first analog computer, a mechanical device that performs calculations by manipulating geometric relationships rather than numerical operations. These ancient instruments possess an almost magical quality. By rotating bronze discs marked with careful engravings, an astronomer can effectively travel forward or backward through time, seeing how the night sky appeared in the past or will appear in the future. The same principle of mechanical computation will eventually evolve into digital computers capable of calculating trajectories for objects arriving from distant stars. Eratosthenes measures Earth's circumference using shadows cast by vertical posts at noon on the summer solstice. His technique requires careful coordination between observers in Alexandria and Syene, measurements that must be synchronized across hundreds of miles of desert terrain. The result, approximately 25,000 miles around Earth's equator, differs from modern measurements by less than 2%. More remarkably, his calculation proves that mathematical reasoning combined with systematic observation can reveal truths about the physical universe that no single human being could discover through direct experience. The library accumulates star catalogs from Babylon, Rhodes, Alexandria, and distant observatories throughout the Greek world. Scholars develop standardized methods for combining observations made at different locations and times, creating the first truly international database of astronomical knowledge. They discover that stars visible from Egypt remain invisible from northern Greece, proving that Earth's surface curves away from the observer in all directions. Ptolemy, working 3 centuries after Hipparchus, synthesizes Greek geometric methods with Babylonian observational data to create the Almagest, a comprehensive mathematical model of planetary motion that will dominate astronomy for 1400 years. His system of epicycles and deferents, though ultimately incorrect in its Earth-centered assumptions, demonstrates mathematical sophistication that will not be surpassed until the Renaissance. Yet the most profound Greek contribution may be methodological rather than technical. They establish the principle that natural phenomena must be explicable through mathematical reasoning. No longer content to accept that planets simply wander according to divine whim. Greek astronomers insist that celestial motions follow discoverable geometric laws. This philosophical commitment to mathematical explanation creates the intellectual foundation for all subsequent astronomical research. The geometric models developed in Alexandria encode something remarkable: predictive algorithms that can be executed by hand calculation. An astronomer equipped with Ptolemaic tables can calculate planetary positions decades in advance using nothing more than careful arithmetic and geometric construction. The same algorithmic thinking that enables these ancient predictions will eventually power computer programs designed to detect objects on hyperbolic trajectories approaching from interstellar space. As afternoon shadows lengthen across the marble floors, Hipparchus completes another set of calculations. His geometric models predict that Venus will reach maximum eastern elongation in precisely 43 days, appearing as evening star at its greatest angular distance from the setting sun. The prediction rests on mathematical principles that will guide human understanding of celestial mechanics for millennia to come. Somewhere within those elegant geometric relationships, encoded in the precise language of circles and angles, lie the mathematical pathways through which cosmic visitors might one day travel toward our waiting world. The Greeks cannot imagine automated telescopes or digital computers, but they establish the conceptual framework that will make both possible: the conviction that mathematical reasoning can penetrate the deepest mysteries of cosmic motion. Only took them 6 centuries to transform Babylonian observations into predictive mathematical models. Only required geometric reasoning and careful measurement to lay the foundations for celestial navigation. Only needed bronze instruments and papyrus scrolls to encode the algorithmic principles that would eventually guide robotic detection systems scanning for visitors from distant stars. The call to prayer echoes across the rooftops of Baghdad as the last light of day fades behind the western horizon, in the House of Wisdom, that great repository of human knowledge built beside the Tigris River. Islamic scholars gather their astrolabes and quadrants for another night of celestial observation. The year drifts near 850 CE, and here, in the heart of the Abbasid Caliphate, the patient work of astronomical refinement continues under different stars. Guided by new hands, but following the same eternal principles that drove Babylonian priests and Greek geometers, Al-Battani adjusts the brass rings of his armillary sphere, its multiple circles representing the fundamental planes of celestial motion: the ecliptic, the celestial equator, the horizon as seen from Baghdad's latitude. The instrument weighs nearly 40 pounds. Constructed from bronze alloy that will not expand or contract significantly with temperature changes, each ring bears engravings precise to fractions of degrees, markings that represent years of careful calibration against known star positions. The Islamic Golden Age brings unprecedented precision to astronomical observation. Where the Greeks worked primarily with geometric theory, the Islamic astronomers focus on measurement accuracy. They understand that small errors in fundamental observations cascade through all subsequent calculations, producing predictions that drift away from reality over time. Their goal is not merely to understand celestial motion, but to perfect the mathematical tools needed for practical applications: navigation, timekeeping, calendar reform, the precise determination of prayer times and religious festivals. Ibn al-Haytham, known in the Latin West as Al-Hazen, revolutionizes observational technique through systematic study of atmospheric refraction. He realizes that Earth's atmosphere bends starlight, causing celestial objects to appear slightly higher in the sky than their true positions. This effect becomes more pronounced near the horizon, where atmospheric density is greatest. By measuring refraction at different altitudes throughout the night, he develops correction tables that improve stellar position measurements by factors of 10 or more. The atmospheric studies reveal something profound about the relationship between observer and observed. Every astronomical measurement is filtered through Earth's gaseous envelope, distorted by temperature gradients and pressure variations that change from hour to hour. The Islamic astronomers learn to compensate for these effects, but they also recognize a deeper principle: that observation itself is always mediated, always influenced by the environment through which information travels from distant objects to human eyes. In the observatory of Isfahan, Al-Zarqali constructs the most accurate astrolabe yet created. an instrument so precise that European astronomers will copy its design for centuries without improvement. The device incorporates corrections for atmospheric refraction, adjustments for the observer's latitude, and tables that account for the gradual precession of Earth's rotational axis. With skilled use, the instrument can determine star positions accurate to within minutes of arc, precision approaching the limits of naked eye observation. The Islamic astronomers inherit star catalogues from Greek and Indian sources, but they quickly discover systematic errors in the older observations. Stellar positions recorded by Ptolemy show significant discrepancies when compared with contemporary measurements. Initially, the scholars assume their own instruments must be flawed. Gradually, however, they realize that the discrepancies result from proper motion, the slow drift of individual stars across the celestial sphere over periods of centuries. This discovery transforms human understanding of stellar nature. The fixed stars are not actually fixed. They move through space with velocities that can be detected through careful comparison of observations separated by many centuries. The realization that stars possess individual motions independent of Earth's rotation or orbital motion suggests that stellar space contains dynamic processes occurring on timescales far longer than human experience. Al-Sufi creates the most comprehensive star catalogue of the medieval period, recording positions and brightness estimates for over 1,000 individual stars. His work includes the first recorded observation of the Andromeda Galaxy, which he describes as a faint star visible to the naked eye under exceptional observing conditions. He cannot know that this dim smudge represents an entire galaxy containing hundreds of billions of stars, but his careful notation of its position and appearance establishes the observational foundation for future discoveries. The Islamic tradition emphasizes institutional continuity across generations. Observatories become permanent establishments with dedicated staff, standardized instruments, and systematic programs of long-term measurement. The Marageh Observatory in Persia maintains continuous observations for over a century, creating datasets that span multiple human lifetimes. This institutional approach enables detection of phenomena, like stellar proper motion or the precession of planetary orbits, that cannot be discovered within individual careers. Ibn Rushdi, known in Europe as Averroes, develops sophisticated models of planetary motion that anticipate later European discoveries by centuries. His mathematical descriptions of Mercury and Venus incorporate elliptical rather than circular orbits, geometric innovations that will not be independently rediscovered until Kepler's work in the early 17th century. The models emerge from careful analysis of Islamic observational data, mathematical reasoning applied to measurements of unprecedented accuracy. The scholars develop new instruments with capabilities that surpass anything previously available. The mural quadrant built in Samarkand stands 40 feet tall, its bronze arc marked with divisions accurate to single minutes of arc. Observations made with this instrument achieve precision levels that will not be exceeded until the invention of the telescope. The quadrant enables measurement of stellar parallax, the apparent shift in star positions caused by Earth's orbital motion. Though the detected shifts are so small, they approach the limits of instrumental accuracy. Navigation emerges as a practical application that drives continued refinement of astronomical techniques. Islamic merchants and explorers travel trade routes spanning from Spain to Indonesia, journeys that require accurate determination of position using celestial observations. The astrolabe becomes an essential tool for maritime navigation, its brass plates encoding the mathematical relationships needed to convert star sightings into geographic coordinates. Al-Kindi develops theoretical frameworks for understanding how astronomical cycles influence terrestrial phenomena. His studies of planetary conjunctions and oppositions reveal correlations with climate patterns, seasonal weather variations, and the timing of natural disasters. While some of his conclusions venture into what modern science would consider astrology, his methodological approach systematic correlation of celestial and terrestrial observations, establishes principles that will guide scientific investigation for centuries. The Islamic astronomers make crucial corrections to fundamental constants inherited from Greek sources. They refine measurements of Earth's circumference, the length of the tropical year, the rate of axial precession, and the orbital periods of all known planets. These improved values propagate through all subsequent astronomical calculations, providing more accurate foundations for predictive models and navigation systems. Perhaps most remarkably, they begin to develop concepts of cosmic evolution. By studying the gradual changes in stellar positions and planetary orbital elements, Islamic scholars recognize that the celestial sphere itself evolves over time. The universe is not static and unchanging, as Greek philosophy generally assumed, but dynamic, subject to processes that operate over time, scales vastly longer than human experience, but still detectable through careful measurement. The work requires extraordinary dedication to precision. A single measurement of a star's position might involve hours of careful observation using multiple instruments, with results checked against previous measurements made years or decades earlier. The accumulated datasets grow to enormous size by medieval standards, thousands of observations recorded on paper made from plant fibers that will preserve the information for centuries. Omar Khayyam, better known in the West for his poetry, contributes astronomical calculations of remarkable sophistication. His determination of the length of the tropical year, 365.2422 days, differs from modern measurements by less than 30 seconds. This precision requires observational techniques and mathematical methods that approach the theoretical limits of pre-telescopic astronomy. The Islamic tradition establishes global networks of astronomical observation. Scholars in Cordoba correspond with colleagues in Damascus and Isfahan, sharing measurements and comparing results obtained at different geographic locations. They discover that certain astronomical phenomena, like meteor showers or cometary appearances, can be observed simultaneously from widely separated locations, providing the first empirical evidence that such events occur at cosmic rather than atmospheric altitudes. By the 12th century, Islamic observatories produce ephemeris tables that predict planetary positions centuries into the future with accuracy that will not be significantly improved until the modern era. These tables incorporate all the observational refinements and mathematical innovations developed during 4 centuries of systematic research. They represent the culmination of pre-telescopic astronomy, achievements that establish the theoretical and practical foundations for all subsequent astronomical investigation. The scholars cannot imagine digital computers or automated telescopes, but they perfect the methodological approaches that will make both possible. Their emphasis on measurement accuracy, systematic error correction, and long-term institutional continuity creates the scientific infrastructure needed to detect subtle phenomena that require decades or centuries of patient observation to discover. As the night deepens over Baghdad, al-Battani completes his observations of Mars approaching opposition. His measurements will contribute to orbital tables accurate enough to guide navigation across vast oceanic distances, predictions precise enough to anticipate celestial events years in advance. Somewhere within those mathematical relationships, encoded in brass instruments and recorded on paper that will survive for centuries, lie the computational principles that will eventually enable automated detection of objects arriving from distant stars. Only took them 500 years to perfect the observational techniques inherited from earlier civilizations, only required dedication to precision and institutional continuity to create the most accurate astronomical databases in human history. Only needed brass instruments and mathematical reasoning to establish the methodological foundations that would eventually guide robotic systems scanning for cosmic visitors, approaching from the depths of interstellar space. The stars wheel overhead in their eternal dance, each position now measured with unprecedented accuracy. each motion recorded for future generations to analyze and understand. The bells of Frombork Cathedral toll midnight across the Baltic shore as Nicholas Copernicus climbs the wooden stairs to his private observatory, built into the cathedral's defensive wall. This modest chamber overlooks the Vistula lagoon, where moonlight transforms the water into molten silver. The year moves toward 1530, and here in this remote corner of Poland, a quiet revolution in human understanding begins to unfold, not through new observations, but through a fundamental reordering of cosmic perspective. Copernicus carries an armillary sphere inherited from his studies in Italy, its brass rings worn smooth by decades of use. The instrument embodies 15 centuries of astronomical tradition, its design unchanged since Ptolemy's time. Yet tonight, as he positions the device to mirror the positions of visible planets, something extraordinary happens. The complex dance of epicycles and deferents that once seemed necessary to explain planetary motion suddenly simplifies into elegant geometric harmony. The revelation emerges gradually, built upon thousands of observations made by Islamic and European predecessors. Mars reaches opposition every 26 months, tracing retrograde loops against the stellar background. Venus oscillates between morning and evening appearances, never straying far from the Sun's position. Mercury displays similar behavior on shorter time scales, for 14 centuries. Astronomers have explained these patterns through increasingly elaborate geometric constructions, circles moving along circles, with smaller circles attached to larger ones in complex hierarchical arrangements. Copernicus realizes that all this complexity vanishes if Earth itself moves. Place the Sun at the center of the cosmic system, set Earth in motion along a yearly orbit, and planetary behavior becomes immediately comprehensible. Mars appears to loop backward because Earth overtakes the more distant planet in its faster inner orbit, the same visual effect that causes distant mountains to seem to move backward when observed from a passing vehicle. Venus remains close to the Sun because she orbits closer to our central star than Earth does. Mercury's rapid oscillations result from his even shorter orbital period. The heliocentric model transforms every subsequent observation into confirmation of cosmic motion. When Jupiter appears to move more slowly through the zodiac than Mars, this indicates Jupiter's greater distance from the Sun and correspondingly longer orbital period. When Venus shows phases like the Moon, crescents, quarters, and full illumination, this reveals her position relative to Earth and Sun in three-dimensional space. The entire solar system becomes a vast clockwork mechanism whose behavior follows mathematical laws rather than arbitrary divine intervention. Yet the Copernican revolution carries implications far beyond improved astronomical predictions. By removing Earth from the center of creation, the new model fundamentally alters humanity's cosmic perspective. We are not stationary observers around whom the universe revolves, but passengers on a moving world orbiting an ordinary star. This philosophical reorientation prepares human consciousness for even more radical discoveries: that our Sun represents just one star among billions, that our galaxy is just one galaxy among countless others, that the universe contains depths of space and time beyond anything previously imagined. The shift in perspective affects how we interpret celestial visitors. In the geocentric model, comets and unusual astronomical phenomena appear as divine portents sent specifically for human interpretation. In the heliocentric system, such objects become natural inhabitants of solar space, following predictable orbits determined by gravitational forces rather than supernatural intervention. This conceptual change creates the intellectual framework needed to understand interstellar objects as physical visitors from distant stellar systems rather than mystical harbingers. Copernicus recognizes that his model requires Earth to move through space at enormous velocity, approximately 67,000 miles per hour, in its orbit around the Sun. This speed seems impossible to reconcile with everyday experience. If Earth truly races through space at such tremendous velocity, why do we feel no wind? Why do objects dropped from towers fall straight down rather than being left behind? These questions will not receive satisfactory answers until Newton develops his laws of motion and gravitation a century and a half later. The heliocentric model also predicts that nearby stars should show parallax shifts as Earth orbits the Sun. Throughout the year, our changing position should cause the apparent positions of close stars to shift slightly against the background of more distant ones. Copernicus searches for this effect but fails to detect it, leading him to conclude that even the nearest stars lie impossibly far from our solar system. The actual measurement of stellar parallax will wait until the 19th century, when telescopic precision finally becomes adequate to detect shifts measured in fractions of arc-seconds. In the quiet hours before dawn, Copernicus works through mathematical calculations that will occupy the remainder of his lifetime. The heliocentric model eliminates much of the geometric complexity required by Ptolemaic astronomy, but accurate predictions still demand careful computation of orbital positions and planetary configurations. He develops tables that predict conjunctions, oppositions, and eclipses with accuracy comparable to the best Islamic ephemerides, demonstrating that the new model provides practical as well as theoretical advantages. The printing press, invented during Copernicus's lifetime, enables rapid dissemination of astronomical knowledge across European centers of learning. His treatise, De Revolutionibus Orbam Coelestium, reaches scholars throughout the continent within decades of publication, sparking debates that will continue for generations. The same technology that spreads the heliocentric model will eventually enable global coordination of astronomical observations, creating communication networks that allow instantaneous sharing of discoveries about objects approaching from interstellar space. Galileo Galilei, working with the newly invented telescope 8 decades after Copernicus's death, provides the first direct observational evidence for the heliocentric model. Jupiter's 4 largest moons orbit their parent planet exactly as Copernican theory predicts smaller worlds should behave. Venus displays phases that prove she orbits the Sun rather than Earth. The Milky Way resolves into countless individual stars, revealing that our solar system inhabits a vast stellar community rather than standing alone at the center of creation. The telescopic discoveries confirm Copernican predictions while revealing new mysteries. Saturn appears to have ears or handles, structures that later prove to be an extensive ring system. Mars shows polar ice caps and seasonal color changes that suggest a world somewhat similar to Earth. The Moon's surface displays mountains, craters, and vast plains, proving that celestial bodies possess complex geology rather than the perfect spherical form assumed by ancient philosophy. Kepler, analyzing precise observations of Mars made by Tycho Brahe, discovers that planetary orbits are elliptical rather than circular. This finding completes the Copernican revolution by eliminating the last remnants of classical geometric assumptions about celestial motion. Planets follow oval-shaped paths whose geometry can be described by mathematical equations, moving faster when close to the Sun and slower when distant. The same orbital mechanics that govern planetary motion will eventually describe the trajectories of comets, asteroids, and visitors from other stellar systems. Newton synthesizes the observational discoveries of Galileo and Kepler with mathematical principles that explain why the heliocentric model works. Universal gravitation provides the physical mechanism that keeps planets in their orbits, describes the motion of comets through the outer solar system, and predicts the existence of undiscovered worlds whose gravitational influence can be detected through perturbations in known planetary motions. The mathematical framework Newton develops will eventually enable calculation of trajectories for objects arriving from interstellar space. The Copernican revolution establishes a crucial precedent for scientific thinking, When observational evidence conflicts with common sense experience, careful mathematical analysis can reveal hidden truths about natural phenomena. This principle guides all subsequent astronomical research, from the discovery of stellar parallax to the detection of exoplanets orbiting distant stars. The same willingness to question fundamental assumptions enables modern astronomers to recognize that some celestial visitors originate from beyond our solar system. As morning twilight brightens the eastern sky above the Vistula Lagoon, Copernicus completes another night's calculations. His geometric models predict that Venus will reach inferior conjunction in 17 days. Passing between Earth and Sun before emerging as morning star in the eastern sky, the prediction rests on mathematical principles that fundamentally redefine humanity's place in the cosmic order. Somewhere within that reordered perspective, encoded in the elegant relationships between moving worlds, lies the conceptual framework needed to understand visitors from distant stars. The universe is not a static hierarchy centered on Earth, but a dynamic system of worlds orbiting suns, with vast spaces between stellar systems through which objects might travel across interstellar distances. Only took 2 millennia to discover that Earth moves through space rather than standing still at the cosmic center. Only required the courage to question fundamental assumptions inherited from ancient authorities. Only needed mathematical reasoning and careful observation to reveal that our world participates in cosmic motions spanning scales far larger than human experience directly perceives. The stars fade into the growing light of dawn, each one now understood as a potential sun around which other worlds might orbit. Other civilizations might evolve. Other visitors might begin journeys that lead eventually towards our small blue planet. Apple trees cast dappled shadows across the garden at Woolsthorpe Manor as Isaac Newton sits beneath their spreading branches, a leather-bound notebook balanced on his knees. The year moves through 1687, and the young mathematician has just completed the most revolutionary scientific treatise in human history, the Principia Mathematica. Though he does not yet fully comprehend how profoundly his mathematical discoveries will reshape our understanding of cosmic motion and celestial visitors. The notebook contains equations that appear deceptively simple, yet describe forces operating across unimaginable distances. Every mass in the universe attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This single mathematical relationship explains why planets orbit the sun, why moons circle planets, why comets trace elongated ellipses through the outer solar system, and why objects dropped from towers fall straight toward Earth's center. Newton's law of universal gravitation emerges from careful analysis of Kepler's observations of planetary motion combined with Galileo's studies of terrestrial mechanics. The mathematical formulation requires Newton to invent an entirely new form of mathematics, calculus, capable of describing continuously changing quantities like velocity and acceleration. The same mathematical tools he develops to analyze planetary orbits will eventually enable calculation of trajectories for spacecraft navigating between worlds and objects arriving from distant stellar systems. The gravitational force operates instantaneously across any distance, no matter how vast. This presents conceptual difficulties that Newton acknowledges but cannot resolve. How can the sun influence Earth's motion across 93 million miles of apparently empty space? What mechanism transmits gravitational force through the void between celestial bodies? These questions will perplex physicists for centuries until Einstein develops his theory of curved space-time. But Newton's mathematical description of gravitational effects proves accurate enough to guide astronomical calculations for 300 years. Universal gravitation reveals that the same physical laws operating on Earth also govern motion throughout the cosmos. The force that causes an apple to fall from a tree branch also keeps the moon in its orbit around Earth, guides Jupiter through its 12-year journey around the sun, and determines the complex paths followed by comets as they approach from the outer reaches of the solar system. This unification of terrestrial and celestial physics represents one of the greatest intellectual achievements in human history. The mathematical framework Newton establishes enables prediction of celestial events with unprecedented precision. His calculations of lunar motion account for gravitational perturbations caused by the sun's influence, producing eclipse predictions accurate to within minutes. His analysis of cometary orbits demonstrates that these mysterious visitors follow natural laws rather than appearing through supernatural intervention. The same predictive capabilities will eventually enable astronomers to calculate when and where objects from interstellar space might become visible in Earth's skies. Edmund Halley applies Newtonian mechanics to historical records of cometary appearances, discovering that bright comets observed in 1531, 1607, and 1682 represent return visits of the same object following a 76-year orbital period. This breakthrough proves that at least some comets are permanent members of the solar system rather than one-time visitors from unknown regions. Halley's successful prediction of the comet's 1758 return provides dramatic confirmation of gravitational theory while establishing the concept that celestial visitors follow calculable schedules. The gravitational analysis reveals extraordinary features of cometary motion. These objects approach the Sun from distances measured in tens of thousands of astronomical units, regions so remote that sunlight requires months to travel from our star to the comet's nucleus. At such distances, gravitational forces are incredibly weak, yet sufficient to guide these icy wanderers through their immense elliptical orbits. The same gravitational architecture that captures comets from the outer solar system could potentially influence objects arriving from even greater distances, from other stellar systems entirely. Newton's laws predict the existence of undiscovered worlds whose gravitational influence can be detected through perturbations in known planetary motions. Uranus, discovered by William Herschel in 1781, follows an orbit that deviates slightly from Newton's calculations. This discrepancy leads to the mathematical prediction and subsequent telescopic discovery of Neptune in 1846, demonstrating that gravitational theory can reveal the presence of invisible objects through their effects on visible ones. The same technique will eventually enable detection of exoplanets orbiting distant stars and dark matter influencing galactic rotation. The mathematical methods Newton develops for analyzing planetary motion apply equally well to projectile trajectories, enabling calculation of paths followed by cannonballs, rockets, and eventually spacecraft. The same equations that describe Earth's orbit around the Sun also determine the velocity needed for a rocket to escape Earth's gravitational influence entirely. This mathematical connection between terrestrial ballistics and celestial mechanics creates the theoretical foundation for space exploration and interplanetary navigation. Universal gravitation explains the tides through differential gravitational forces exerted by the Moon and Sun on Earth's oceans. The same tidal effects operate on all celestial bodies, causing Jupiter's moons to experience internal heating through gravitational flexing, creating geysers on Saturn's moon Enceladus, and potentially affecting the internal structure of any object passing close to massive celestial bodies. These gravitational interactions could influence the behavior of interstellar visitors as they approach our solar system. The Newtonian framework reveals that orbital mechanics operates according to conservation laws, mathematical principles stating that certain quantities remain constant throughout complex gravitational interactions. Conservation of energy determines whether an object possesses sufficient velocity to escape from a gravitational system entirely, while conservation of angular momentum explains why comets move faster when close to the Sun and slower when distant. These same conservation principles govern the motion of objects traveling between stellar systems. Newton's analysis of lunar motion demonstrates that gravitational forces from multiple sources combine in mathematically predictable ways. The Moon's orbit around Earth is continuously perturbed by the Sun's gravitational field, creating complex variations in orbital speed, shape, and orientation. This multi-body gravitational problem requires sophisticated mathematical techniques to solve, methods that will eventually enable calculation of spacecraft trajectories through gravitational fields created by multiple planets and moons. The mathematical precision of Newtonian mechanics enables detection of extremely subtle gravitational effects. Measurements of planetary positions accurate to arc seconds reveal orbital perturbations caused by gravitational interactions between different worlds. The same mathematical sensitivity that detects Neptune's influence on Uranus could potentially identify gravitational signatures of objects approaching from interstellar space, if their masses are sufficiently large and their approach trajectories bring them close enough to known planetary orbits. Pierre-Simon Laplace extends Newtonian analysis to demonstrate that the solar system's configuration exhibits long-term stability, despite complex gravitational interactions between multiple planets. The overall orbital architecture remains stable over time, scales spanning millions of years. This mathematical proof suggests that the solar system can accommodate occasional visitors from interstellar space without experiencing fundamental disruption, provided such objects do not possess extremely large masses or highly unusual trajectories. The gravitational framework Newton establishes applies to systems of any scale, from binary star systems to galaxy clusters. The same mathematical principles that describe planetary motion around the Sun also govern the orbital dynamics of stellar pairs, the rotation of galaxies, and the large-scale structure of the universe itself. This universality of gravitational law creates the theoretical foundation for understanding how objects might travel between stellar systems under the influence of gravitational forces operating across vast distances. As afternoon shadows lengthen across the garden at Woolsthorpe, Newton completes another series of calculations predicting the precise timing of the next lunar eclipse. His mathematical model accounts for gravitational perturbations that shift the Moon's position by tiny amounts, corrections that improve eclipse predictions by minutes or hours compared to earlier astronomical tables. The same mathematical sophistication that enables such precise lunar calculations could eventually guide detection algorithms designed to identify objects approaching Earth from interstellar space, somewhere within those elegant mathematical relationships, encoded in equations that describe invisible forces operating across cosmic distances, lie the computational tools needed to calculate trajectories for any object moving under gravitational influence. The universe operates according to mathematical laws precise enough to predict celestial events centuries in advance, consistent enough to guide navigation across interplanetary distances, universal enough to describe motion throughout the cosmos. Only took one mathematical genius to reveal that the same forces operating in English gardens also govern motion throughout the universe. Only required the invention of calculus and careful analysis of planetary observations to establish gravitational theory. Only needed mathematical reasoning and physical insight to create the computational framework that would eventually enable prediction and detection of visitors traveling towards our solar system from distant stars. The glass plates rest in neat stacks beside the telescope, their silver emulsion surfaces bearing the accumulated light of distant stars captured during long exposure nights at Harvard College Observatory. The year moves through 1885, and here in the growing industrial city of Cambridge, Massachusetts, astronomy begins its transformation from visual observation to photographic recording, a technological revolution that will fundamentally alter humanity's ability to detect moving objects against the stellar background. Edward Pickering adjusts the clockwork mechanism that keeps the telescope precisely aligned with Earth's rotation, compensating for our planet's motion so that stellar images remain fixed on the photographic plate throughout exposures lasting several hours. This technique enables detection of far fainter stars than visual observation could ever reveal. But it also creates something unprecedented: permanent records of the night sky that can be compared across decades or centuries to detect subtle changes invisible to human perception. The photographic plates capture not just stellar positions, but stellar motions. By comparing images taken months or years apart, astronomers can detect the proper motion of individual stars, their gradual drift across the celestial sphere over time. More importantly, they can identify objects that move much faster than normal stars, objects that change position significantly between successive photographs. These rapid movers reveal themselves as comets, asteroids, or other members of our solar system traveling against the distant stellar background. Maria Mitchell, working at Vassar College Observatory, discovers that photographic techniques can reveal details invisible to visual observation. Stellar spectra, the rainbow patterns created when starlight passes through a prism, show absorption lines that indicate the chemical composition of distant suns. Some stars contain elements identical to those found on Earth, while others display unusual spectral features that suggest exotic compositions or extreme physical conditions. The same spectroscopic techniques that reveal stellar chemistry will eventually enable analysis of the composition and origin of objects visiting our solar system from interstellar space. The Harvard College Observatory begins the most ambitious photographic survey yet attempted: systematic imaging of the entire sky visible from both northern and southern hemispheres. The project requires coordination between observatories in Massachusetts and Peru, with standardized photographic equipment and identical measurement techniques used at both locations. Over decades, this survey creates the first comprehensive photographic atlas of stellar positions, enabling detection of any object that moves against the apparently fixed stellar background. Annie Jump Cannon develops classification systems for stellar spectra that reveal the diversity of stellar types throughout our galaxy. Hot blue stars show different spectral patterns than cool red stars, enabling determination of stellar temperatures from photographic analysis alone. This work establishes that our Sun represents just one example of stellar evolution, that the galaxy contains billions of other suns at different stages of their cosmic life cycles. The realization that stars evolve over time creates the conceptual framework for understanding how planetary systems might form around other stars, potentially creating conditions for life and technological civilizations. The photographic surveys reveal objects that change brightness over time, variable stars whose luminosity fluctuates according to discoverable patterns. Henrietta Swan Leavitt, studying Cepheid variables in the Magellanic Clouds, discovers a precise relationship between pulsation period and intrinsic brightness. This discovery provides astronomers with standard candles, objects whose distance can be calculated from their apparent brightness and known intrinsic luminosity. The same measurement techniques will eventually enable determination of distances to objects approaching our solar system from interstellar space. Williamina Fleming, examining thousands of photographic spectra, discovers the first white dwarf star, a stellar remnant so dense that a teaspoonful of its material would weigh several tons on Earth. This discovery reveals that stellar evolution can produce objects with physical properties far beyond anything found in our solar system. The existence of such exotic stellar remnants suggests that interstellar space might contain visitors with compositions and structures unlike any objects native to our cosmic neighborhood. The photographic plates accumulate in climate-controlled storage rooms, creating the first permanent archives of astronomical observations. These glass libraries preserve images that can be re-examined decades later with improved measurement techniques or theoretical understanding. Future astronomers will discover objects in these historical photographs that were invisible to the original observers. demonstrating that systematic archival of observational data can yield discoveries long after the initial observations are made. Max Wolf, working at Heidelberg Observatory, develops the first photographic method for systematic asteroid discovery. By comparing photographs taken several hours apart, he can identify objects that move perceptibly against the stellar background during a single night. This blink comparator technique enables detection of asteroids too faint for visual observation, revealing that our solar system contains thousands of small worlds orbiting between Mars and Jupiter. The same photographic comparison methods will eventually enable detection of objects on unusual trajectories that might originate from outside our solar system. The photographic revolution coincides with improvements in telescope design that enable capture of much fainter objects than visual observation could detect. Large reflector telescopes with mirrors measured in feet rather than inches gather sufficient light to photograph stars invisible to the naked eye. These instruments reveal that the Milky Way contains far more stars than previous estimates suggested, and that many nebulae thought to be gaseous clouds are actually distant star clusters, or galaxies composed of billions of individual suns. Percival Lowell establishes Lowell Observatory in the clear. Dry air of Flagstaff, Arizona, specifically for photographic studies of planetary surfaces and the search for undiscovered worlds. His systematic photography of Mars reveals seasonal changes in surface features that suggest possible biological activity, though later analysis will show these changes result from dust storms and atmospheric phenomena rather than vegetation. The same patient photographic monitoring techniques Lowell develops for planetary observation will eventually enable detection of objects approaching our solar system from interstellar distances. The photographic surveys begin to reveal the three-dimensional structure of our galaxy. Stars near the galactic plane show different proper motions than stars located above or below the Milky Way's central disk, indicating that our stellar system possesses complex internal dynamics. This discovery suggests that stars and planetary systems move through the galaxy along predictable trajectories, creating opportunities for gravitational encounters between stellar systems that might occasionally eject objects into interstellar space. Friedrich Argelander completes the Bonner Durchmusterung, a photographic catalog containing positions and brightness measurements for over 300,000 stars. This database enables detection of any star that changes position or brightness over time, providing the observational foundation for discovering novae, variable stars, and moving objects within our solar system. The same cataloging principles that enable systematic monitoring of stellar positions will eventually guide automated survey systems designed to detect objects approaching from interstellar space. The Harvard photographic plates reveal that some stars display unusual spectra suggesting motion toward or away from Earth. These Doppler shifts in stellar spectral lines indicate radial velocities that can be measured with remarkable precision. The discovery that stars possess individual motions through space in all three dimensions, not just across the plane of the sky, establishes that our galaxy is a dynamic system where stellar encounters and gravitational interactions continuously reshape the cosmic environment. George Ellery Hale develops new techniques for photographing solar spectra that reveal the sun's chemical composition and physical conditions. His discovery of magnetic fields in sunspots demonstrates that stars possess complex magnetic environments that might influence the behavior of charged particles throughout planetary systems. The same spectroscopic techniques Hale pioneers for solar observation will eventually enable analysis of the composition and physical properties of any object that approaches close enough to our Sun for detailed study. The photographic archives grow to enormous size by early 20th century standards, hundreds of thousands of glass plates storing images of millions of celestial objects. Astronomers develop mechanical devices for measuring stellar positions on these photographs, with precision approaching the limits of photographic grain structure. The same systematic approach to data collection and analysis that characterizes photographic astronomy will eventually enable automated processing of vast datasets generated by electronic imaging systems. As the 19th century draws toward its close, the photographic revolution has fundamentally transformed astronomical observation from sporadic visual studies to systematic monitoring of the entire sky. The accumulated archives contain evidence for stellar evolution, galactic structure, and the dynamic nature of cosmic environments. Most importantly, they establish the methodological foundation for detecting any object that moves against the stellar background, whether asteroids orbiting within our solar system or visitors approaching from the depths of interstellar space. Only took 4 decades to transform astronomy from visual observation to photographic recording. Only required glass plates and clockwork mechanisms to create permanent archives of celestial images. Only needed systematic comparison of photographs taken at different times to enable detection of moving objects invisible to direct human observation. The vacuum tubes glow softly in the darkened laboratory at Bell Laboratories, their amber filaments casting warm light across arrays of electronic equipment that represent the cutting edge of mid-20th century technology. The year moves through 1969, and here in the industrial corridors of New Jersey, the charge-coupled device begins its transformation from experimental curiosity to the technological foundation that will revolutionize astronomical observation and enable detection of the faintest moving objects against the stellar background. Willard Boyle and George Smith adjust the voltage levels across silicon wafer surfaces etched with microscopic wells, each cavity capable of accumulating electric charge proportional to the intensity of light striking its surface. The CCD operates on quantum mechanical principles. Individual photons striking silicon atoms liberate electrons that accumulate in potential wells created by carefully controlled electric fields. This electronic process converts light directly into digital information without the chemical intermediaries required by photographic emulsion. The electronic imaging system possesses sensitivity far exceeding photographic plates. Where film might capture 1% of incident photons, CCDs can detect and record more than 80% of the light striking their surfaces. This dramatic improvement in quantum efficiency enables detection of objects hundreds of times fainter than photographic limits, revealing previously invisible asteroids, comets, and stellar phenomena that were beyond the reach of earlier observational techniques. The CCD arrays can be manufactured with millions of individual light-sensitive elements, each pixel capable of independent measurement and electronic readout. This creates imaging systems with spatial resolution far exceeding photographic grain structure, enabling detection of moving objects that would appear as mere smudges on glass plates. The electronic format also allows real-time processing of observational data, making possible automated detection of objects that change position between successive images. James Westphal, adapting CCD technology for astronomical use at California Institute of Technology, realizes that electronic imaging enables entirely new observational strategies. Unlike photographic plates that require chemical development after exposure, CCDs provide immediate access to digital image data that can be processed by computer algorithms. This real-time capability enables automated comparison of successive images to detect moving objects within minutes rather than hours or days. The electronic revolution coincides with development of computer systems powerful enough to process vast amounts of digital image data. The same silicon technology that creates sensitive CCD arrays also enables construction of digital computers capable of storing, analyzing, and comparing millions of astronomical measurements. This convergence of electronic imaging and computational analysis creates the technological foundation for automated sky surveys that can monitor the entire visible sky simultaneously. Eugene Shoemaker, working with electronic imaging systems at Palomar Observatory, develops systematic techniques for asteroid and comet discovery using CCD arrays. His methods involve taking multiple images of the same sky region separated by intervals of several hours, then using computer software to identify objects that move between successive exposures. This automated approach enables detection of hundreds of previously unknown solar system objects, revealing that our cosmic neighborhood contains far more small bodies than visual or photographic surveys had detected. The electronic imaging systems reveal details of cometary structure invisible to earlier observational methods. CCD arrays can detect the faint ion tails that extend millions of miles behind comet nuclei, trace the complex interaction between solar wind and cometary material, and monitor variations in brightness that occur as rotating nuclei expose different surface regions to sunlight. These observations establish that comets are complex objects with internal structure and dynamic behavior that varies throughout their orbital periods. Linear CCD arrays enable development of drift scan observing techniques that can monitor vast areas of sky continuously. Rather than pointing telescopes at specific targets, these systems allow the sky to drift across electronic detectors as Earth rotates, creating continuous strips of sky coverage that can detect any object moving against the stellar background. This approach maximizes the volume of space monitored per unit time, dramatically increasing the probability of detecting rare events like interstellar visitors. The Hubble Space Telescope, launched in 1990 with advanced CCD imaging systems, demonstrates the extraordinary capabilities of electronic astronomy operating above Earth's atmospheric interference. Its images reveal details of stellar formation, planetary nebulae, and galactic structure that were impossible to observe from ground-based observatories. The same electronic imaging technology that enables Hubble's discoveries also makes possible sensitive monitoring of near-Earth space for objects approaching from any direction. Astronomical CCD systems begin incorporating specialized features for time-domain observations. Electronic shutters can expose individual pixels for precisely controlled intervals, enabling measurement of rapidly varying phenomena like stellar occultations or asteroid rotations. Cooling systems reduce electronic noise to levels approaching fundamental quantum limits, maximizing sensitivity to faint objects. These technical improvements create imaging systems capable of detecting objects that would be completely invisible to photographic methods. The digital format of CCD observations enables development of sophisticated image processing techniques. Computer algorithms can subtract background starlight to reveal faint extended structures around celestial objects, enhance contrast to detect subtle variations in surface brightness, and combine multiple exposures to increase effective sensitivity beyond what any single observation could achieve. These same processing techniques will prove essential for extracting maximum information from observations of interstellar visitors. The Sloan Digital Sky Survey, beginning operations in the late 1990s, demonstrates the power of large-scale electronic astronomy combined with automated data processing. This project uses specialized CCD cameras to systematically image approximately 1/4 of the entire sky, creating digital maps containing hundreds of millions of celestial objects. The survey's automated pipeline processes terabytes of observational data, identifying galaxies, quasars, asteroids, and variable stars through computer analysis of electronic images. Electronic imaging systems enable discovery of objects with unusual spectral properties that might indicate exotic compositions or extreme physical conditions. CCDs can detect near-infrared radiation invisible to photographic emulsion, revealing thermal emission from asteroids and comets that provides information about their internal temperatures and surface compositions. The same spectroscopic capabilities that characterize solar system objects could potentially identify visitors from other stellar systems through analysis of their unique chemical signatures. The Wide Field Infrared Survey Explorer, WISE, uses advanced CCD arrays cooled to near absolute zero to detect thermal radiation from asteroids, comets, and brown dwarf stars throughout our solar system and beyond. This space-based observatory discovers thousands of previously unknown objects, including asteroids on potentially hazardous orbits that bring them close to Earth. The survey techniques WISE demonstrates establish the methodological foundation for detecting any object that enters our solar system, regardless of its origin. The Kepler Space Telescope employs ultra-sensitive CCD arrays to monitor the brightness of over 100,000 stars simultaneously, searching for periodic dimming events that might indicate transiting exoplanets. This mission demonstrates that electronic imaging systems can detect incredibly subtle variations in stellar brightness, changes of less than 0.01% that occur when distant planets pass in front of their parent stars. The same photometric precision could potentially detect brightness variations in objects approaching our solar system from interstellar distances. Ground-based surveys, like the Catalina Sky Survey, use networks of CCD-equipped telescopes to monitor large portions of the sky every night, systematically searching for objects that move against the stellar background. These automated systems can process thousands of images per night, comparing successive observations to identify asteroids, comets, and any other objects that change position over time. The software algorithms developed for these surveys create the computational foundation for detecting interstellar visitors. The electronic revolution transforms astronomical observation from occasional targeted studies to continuous monitoring of cosmic environments. CCD arrays enable construction of robotic observatories that operate autonomously, collecting data throughout every clear night and processing observations automatically to identify interesting phenomena. This systematic approach to sky monitoring maximizes the probability of detecting rare events that occur unpredictably. Modern CCD systems incorporate on-chip electronics that can perform preliminary data analysis in real time, flagging unusual observations for immediate human attention. These smart detectors can identify moving objects, variable stars, or transient phenomena within minutes of observation, enabling rapid follow-up studies of interesting discoveries. The same real-time processing capabilities that characterize current electronic imaging systems provide the technological foundation for automated detection of objects approaching from interstellar space. Only took 2 decades to replace photographic plates with electronic imaging systems thousands of times more sensitive. Only required silicon technology and computer processing to enable automated detection of moving objects invisible to earlier observational methods. Only needed the convergence of electronic imaging and digital computation to create observational capabilities that could monitor the entire sky continuously for visitors approaching from any direction. Silicon wafers rest in cleanroom environments where the air itself is filtered to remove particles smaller than bacteria. And here, in the sterile laboratories of technology companies scattered across California's Silicon Valley, the algorithms that will one day detect interstellar visitors begin their evolution from simple pattern recognition routines to sophisticated artificial intelligence systems capable of analyzing millions of astronomical observations simultaneously. The year moves through 1995, and computer scientists working for companies like Intel and Digital Equipment Corporation develop image processing algorithms originally designed for industrial quality control, software that can examine manufactured products and automatically identify defects invisible to human inspection. These same pattern recognition principles, adapted for astronomical applications, will eventually enable automated detection of objects moving against the stellar background with sensitivity and speed far exceeding human capabilities. The algorithms operate through mathematical techniques that sound almost mystical in their abstraction. Neural networks inspired by biological brain structure process input data through multiple layers of artificial neurons, each layer extracting increasingly complex patterns from raw observational information. Machine learning systems improve their performance automatically by analyzing thousands of training examples, gradually developing the ability to distinguish genuine astronomical phenomena from instrumental artifacts or data processing errors. Eugene Shoemaker and David Levy, working with early computer-assisted detection systems at Palomar Observatory, discover that automated algorithms can identify moving objects in astronomical images with remarkable reliability. Their software compares successive CCD images taken several hours apart, mathematically subtracting stellar backgrounds to reveal any objects that change position between exposures. This technique enables detection of asteroids and comets too faint for visual observation, demonstrating that computer analysis can extend human observational capabilities far beyond biological limits. The pattern recognition algorithms face extraordinary challenges. Astronomical images contain millions of individual stars, galaxies, and cosmic ray artifacts that can mimic the appearance of moving objects. Electronic noise from CCD cameras creates random variations in pixel brightness that might be mistaken for genuine astronomical phenomena. Atmospheric turbulence causes stellar images to shift slightly between successive exposures, requiring sophisticated mathematical techniques to align images precisely before comparing them for moving objects. Linear, Lincoln Near-Earth Asteroid Research Program, operated by MIT's Lincoln Laboratory, developed some of the first fully automated detection systems capable of processing hundreds of astronomical images per night. The software pipeline automatically corrects for instrumental effects, aligns successive images to sub-pixel precision, identifies objects that move between exposures, and classifies detections according to their apparent motion and brightness characteristics. This automated approach enables discovery of thousands of previously unknown asteroids and comets. The algorithms learn to distinguish between different types of moving objects based on their motion characteristics. Asteroids typically move slowly and follow nearly straight paths across the sky over periods of several hours. Comets may show similar motion, but often display extended fuzzy appearances rather than star-like points. Artificial satellites move much faster than natural solar system objects and follow curved paths that reflect their orbital mechanics around Earth. By analyzing these motion signatures, computer algorithms can automatically classify detections into appropriate categories. Computational improvements enable processing of increasingly large datasets. Moore's law drives exponential increases in computer processing speed and memory capacity, making possible analysis of observational surveys that generate terabytes of data each night. Parallel processing techniques distribute computational workloads across networks of computers, enabling real-time analysis of observations from multiple telescopes simultaneously. These technological advances create the computational infrastructure needed to monitor vast volumes of space for rare phenomena like interstellar visitors. The Sloan Digital Sky Survey develops sophisticated algorithms for automated analysis of multicolor astronomical images. The software can distinguish between stars, galaxies, and solar system objects based on their colors, surface brightness profiles, and motion characteristics. Machine learning techniques enable the system to improve its classification accuracy by analyzing millions of training examples, gradually developing the ability to identify unusual objects that don't fit standard categories. Astronomer Tom Gerrels, working with the Spacewatch program at the University of Arizona, pioneers techniques for detecting objects on unusual orbits that might originate from outside our solar system. His algorithms analyze orbital elements calculated from multiple observations of moving objects, identifying trajectories with eccentricities or inclinations that suggest non-solar system origins. This work establishes the computational methods needed to recognize interstellar visitors through their distinctive orbital characteristics. The detection algorithms incorporate increasingly sophisticated statistical techniques. Bayesian analysis enables assessment of detection probabilities based on prior knowledge of object populations and observational selection effects. Monte Carlo simulations test algorithm performance using artificial datasets with known properties, helping developers understand systematic biases and detection limits. These statistical approaches ensure that automated detection systems can reliably distinguish genuine astronomical phenomena from spurious artifacts. Advances in computer graphics processing units, GPUs, originally developed for video games, provide new computational platforms for astronomical image analysis. These specialized processors can perform thousands of mathematical operations simultaneously, dramatically accelerating pattern recognition algorithms that must analyze millions of pixels in astronomical images. The same GPU technology that renders realistic computer graphics enables real-time processing of observational data from multiple telescopes. The Catalina Sky Survey, operating automated telescopes in the mountains of Arizona, develops algorithms that can detect moving objects in real time during observational sequences. Their software processes CCD images as they are acquired, identifying potential discoveries within minutes of observation and automatically scheduling follow-up observations to confirm initial detections. This rapid response capability maximizes the scientific value of each clear night by enabling immediate confirmation of interesting discoveries. Deep learning algorithms, inspired by recent advances in artificial intelligence, begin showing remarkable capabilities for astronomical pattern recognition. Convolutional neural networks can learn to identify subtle features in astronomical images that human observers might miss, distinguishing between genuine celestial objects and various types of instrumental artifacts. These AI systems improve their performance automatically by analyzing vast training datasets, developing superhuman abilities for certain types of astronomical detection tasks. The algorithms learn to compensate for systematic effects that might interfere with detection of unusual objects. Scattered light from bright stars can create artifacts that mimic moving objects in sensitive CCD images. Cosmic ray impacts on electronic detectors produce bright spots that might be mistaken for asteroids or comets. Satellite trails and aircraft contrails leave streaks across astronomical images that could confuse automated detection systems. Sophisticated software learns to recognize and reject these various sources of false detections. Citizen science projects like Galaxy Zoo demonstrate that human pattern recognition capabilities can complement automated algorithms for certain types of astronomical classification tasks. Volunteers examine thousands of galaxy images, identifying unusual structures or phenomena that automated systems might miss. The same human-computer collaboration that characterizes galaxy classification could potentially be applied to detection and analysis of unusual objects approaching our solar system from interstellar space. Modern detection algorithms operate at scales that would have been impossible just decades earlier. The Large Synoptic Survey Telescope, currently under construction, will generate approximately 20 terabytes of astronomical data each night, more information than all previous astronomical surveys combined. Processing this data stream requires automated algorithms capable of identifying interesting phenomena among billions of routine observations, flagging unusual detections for human follow-up study. The algorithms develop increasingly sophisticated capabilities for predicting object behavior based on limited observational data. Orbit determination software can calculate future positions of newly discovered asteroids from just a few nights of observations, enabling targeted follow-up studies of interesting objects. The same predictive capabilities that characterize asteroid orbit calculations could enable rapid assessment of trajectory characteristics for any object detected approaching our solar system from interstellar distances. Only took 3 decades for pattern recognition algorithms to evolve from simple image processing routines to sophisticated artificial intelligence systems. Only required the exponential growth of computational capabilities to enable real-time analysis of vast astronomical datasets. Only needed the convergence of advanced algorithms and powerful computers to create detection systems capable of automatically identifying rare phenomena among billions of routine observations. The tropical trade winds carry the scent of plumeria blossoms and volcanic soil across the slopes of Haleakala, where two dome-shaped structures rise against the star-filled darkness of the Hawaiian night. Here, at an altitude of 10,000 feet above the Pacific Ocean, the Asteroid Terrestrial Impact Last Alert System begins its patient vigil, twin robotic telescopes that will scan the heavens with unprecedented thoroughness, their electronic eyes searching for any object that moves against the seemingly fixed stellar background. The year moves through 2015, and within the Atlas control room, arrays of computer monitors display real-time images streaming from the telescope's sensitive CCD cameras. Each frame captures a section of sky larger than the full moon, and the system acquires new images every few minutes throughout the night, systematically mapping the entire visible sky multiple times each month. This comprehensive survey strategy maximizes the probability of detecting objects on unusual trajectories, including potential visitors from interstellar space. John Tonry, the principal investigator who conceived the Atlas survey, adjusts the software parameters that control automated detection algorithms. The system must balance sensitivity against reliability, detecting objects as faint as possible while avoiding false alarms caused by cosmic rays, satellite trails, or other instrumental artifacts. The algorithms analyze each new image by comparing it with reference frames of the same sky region, mathematically subtracting the background stars to reveal any objects that have moved or changed brightness since previous observations. The Hawaiian location provides extraordinary observational advantages. The dry, stable atmosphere above Haleakala creates exceptionally clear skies with minimal atmospheric turbulence, enabling detection of objects near the theoretical limits of ground-based observation. The isolated Pacific setting reduces light pollution to negligible levels, while the northern tropical latitude allows monitoring of most of the sky visible from Earth's northern hemisphere. These environmental factors combine to create observational conditions approaching those available only from space-based telescopes. The Atlas telescopes themselves represent marvels of automated engineering. Each instrument contains a 0.5-meter mirror that gathers light from celestial objects and focuses it onto CCD arrays containing 100 million individual light-sensitive pixels. Computer-controlled mechanisms automatically adjust focus, track celestial motion, and position the telescope for optimal observations throughout the night. The entire system operates without human intervention, acquiring and processing astronomical data continuously during clear weather conditions. The survey strategy emphasizes rapid cadence observations that can detect objects on fast-moving trajectories. While traditional asteroid surveys might revisit the same sky regions weekly or monthly, Atlas observes each accessible area of sky multiple times per night when possible. This high-frequency monitoring enables detection of objects that change position significantly over periods of hours rather than days, including potential interstellar visitors that might traverse the inner solar system relatively quickly. Larry Deno, the software engineer responsible for the Atlas detection pipeline, develops algorithms that can process the massive data streams generated by continuous sky monitoring. Each night of operations produces hundreds of gigabytes of astronomical images that must be analyzed in real time to identify moving objects before they disappear into the daytime sky. The computational challenge requires sophisticated software architectures that can distribute processing workloads across networks of computers while maintaining the reliability needed for scientific discovery. The detection algorithms face extraordinary discrimination challenges. The typical Atlas image contains approximately 50,000 individual stars, galaxies, and other stationary objects, along with various instrumental artifacts that can mimic astronomical phenomena. Among these millions of routine detections, the software must identify the handful of objects that represent genuine solar system bodies moving against the stellar background. This pattern recognition task requires mathematical techniques that can distinguish subtle motion signatures from random noise and systematic errors. The survey discovers thousands of previously unknown asteroids during its first years of operation, revealing that our solar system contains far more small objects than earlier surveys had detected. Many of these discoveries follow unusual orbits that bring them close to Earth or carry them far from the Sun into the outer reaches of the planetary system. The diversity of orbital characteristics suggests that gravitational processes continuously reshape the population of small bodies throughout our cosmic neighborhood. Robert Werrick, analyzing Atlas data streams, develops specialized techniques for detecting objects with extremely high orbital velocities that might indicate non-solar system origins. Traditional asteroid detection algorithms assume that moving objects follow orbits bound to our Sun, but interstellar visitors would display motion characteristics unlike any native solar system body. The software must search for objects moving faster than escape velocity, following hyperbolic rather than elliptical trajectories, potentially approaching from directions that no solar system comet or asteroid would follow. The automated survey operations continue regardless of weather conditions or human schedules. When skies are clear, the telescopes acquire data continuously from sunset to sunrise, building an ever-growing database of astronomical observations that can be searched for objects displaying unusual motion patterns. When clouds interfere with observations, the detection algorithms continue processing archived data, searching for moving objects that might have been missed during initial real-time analysis. The Atlas data processing pipeline incorporates sophisticated quality control measures that ensure reliable detection of genuine astronomical phenomena. Each potential moving object must be detected in multiple images acquired over several hours before being classified as a confirmed discovery. The software automatically calculates preliminary orbital elements for newly detected objects, enabling prediction of future positions that can be verified through targeted follow-up observations. These verification procedures minimize false discovery rates while maximizing sensitivity to genuine astronomical objects. International collaboration networks enable rapid sharing of Atlas discoveries with observatories worldwide. When the survey detects an object on an unusual trajectory, automated notification systems immediately alert astronomers at other facilities who can provide additional observations needed to determine precise orbital characteristics. This global coordination maximizes the scientific value of each discovery by enabling comprehensive characterization of interesting objects before they become too faint for detailed study. The survey's comprehensive sky coverage creates an observational safety net that can detect objects approaching Earth from any direction. Unlike targeted searches that monitor specific regions of sky where asteroids are most likely to appear, Atlas maintains surveillance over the entire accessible celestial sphere. This all-sky monitoring strategy ensures that unusual objects, including potential interstellar visitors, cannot approach our planet undetected, regardless of their origin or trajectory characteristics. Ken Chambers, leading the data analysis efforts, develops statistical techniques for assessing the significance of unusual discoveries within the vast datasets generated by automated sky surveys. The challenge involves distinguishing genuinely extraordinary phenomena from the statistical fluctuations that inevitably occur when monitoring millions of objects over extended time periods. Bayesian analysis methods enable quantitative assessment of discovery probabilities, helping researchers determine when unusual observations represent truly unprecedented discoveries rather than rare but expected variations in known object populations. The Atlas survey establishes observational baselines that enable detection of changes in the solar system environment over time, scales spanning years or decades, by maintaining consistent monitoring of the same sky regions using identical instrumental techniques. The survey can identify secular changes in object populations, orbital distributions, or activity levels that might indicate external influences on our solar system. These long-term studies provide the observational foundation needed to recognize when interstellar visitors arrive in our cosmic neighborhood, modern improvements in detector technology and data processing capabilities enable increasingly sensitive searches for objects on unusual trajectories. The next generation of survey telescopes will combine larger mirrors with more sensitive electronic detectors and more powerful computational resources, enabling detection of objects too faint or fast-moving for current systems to identify. These technological advances ensure that future sky surveys will possess the sensitivity needed to detect interstellar visitors well before they approach close enough to Earth for detailed study. As the Hawaiian night deepens and the Milky Way reaches its zenith above Haleakala, the Atlas telescopes continue their systematic patrol of the heavens. Their electronic eyes record the positions of millions of celestial objects with precision measured in fractions of arc-seconds, building databases that preserve the current state of our cosmic environment for comparison with future observations. Somewhere within that accumulated observational data lies the capability to recognize when objects from distant stellar systems enter our solar system. Their presence revealed through motion patterns unlike anything native to our cosmic neighborhood. Only took a decade to deploy automated survey systems capable of monitoring the entire sky for moving objects. Only required advanced CCD technology and sophisticated algorithms to enable detection of the faintest possible visitors approaching from any direction. Only needed the convergence of sensitive detectors, powerful computers, and systematic observational strategies to create surveillance systems capable of detecting interstellar visitors before they could approach our planet unobserved. The pixels glow softly on computer monitors throughout the Atlas Operations Center as dawn approaches over the Hawaiian mountains. And within the streams of digital data flowing from the robotic telescopes, a subtle anomaly begins to emerge, an object moving faster than any asteroid should move, following a trajectory that suggests origins far beyond the familiar boundaries of our solar system. The date reads January 29, 2018, and the detection algorithms that have processed millions of routine observations during Atlas's 3 years of operation encounter something unprecedented. Object designation. A10BMLZs appears initially unremarkable. A faint point of light detected in successive images acquired 4 minutes apart, displaying motion consistent with a solar system body somewhere beyond Earth's orbit. Only when additional observations accumulate over the following hours does the object's true nature begin to reveal itself. Robert Werrick, monitoring the automated detection pipeline from his office at the University of Hawaii's Institute for Astronomy, notices the unusual astrometric properties that distinguish this object from thousands of routine asteroid discoveries. The preliminary orbital calculation suggests extremely high eccentricity, mathematical parameters indicating that the object follows a hyperbolic rather than elliptical trajectory. In the terminology of celestial mechanics, this represents an unbound orbit, characteristic of objects with sufficient velocity to escape the sun's gravitational influence entirely. The discovery process unfolds with remarkable precision, demonstrating the sophisticated automation that characterizes modern astronomical surveys. Within minutes of initial detection, Atlas's software calculates approximate coordinates and motion vectors for the new object, automatically scheduling follow-up observations to confirm its reality and refine its orbital characteristics. The system simultaneously searches archival images from previous nights, seeking earlier observations that might have captured the object before its official discovery date. Ken Chambers examines the preliminary orbit solution and recognizes immediately that something extraordinary has been detected. The object's hyperbolic trajectory indicates approach from interstellar space, the first confirmed visitor from beyond our solar system ever detected by human technology. The mathematical evidence is unambiguous. This object possesses more kinetic energy than solar gravity can provide, meaning it must have originated from another stellar system entirely. The discovery triggers immediate international alerts through the International Astronomical Union's electronic notification system. Within hours of initial detection, observatories throughout the world receive automated messages describing the object's coordinates, motion, and preliminary orbital characteristics. This rapid dissemination ensures that astronomers globally can contribute additional observations needed to determine the visitor's precise trajectory and physical properties before it fades beyond detection limits. David Tholen leads the international observational campaign that unfolds during the weeks following discovery. Telescopes from Hawaii to Chile to the Canary Islands track the object continuously, measuring its position with extraordinary precision and monitoring its brightness as it travels outbound from the Sun. Each new observation refines the orbital calculation, gradually revealing the full three-dimensional path the object has followed through our solar system. The orbital analysis reveals remarkable characteristics that distinguish this interstellar visitor from any native solar system object. The trajectory approaches from the direction of the constellation Lyra, suggesting possible origin from the vicinity of the bright star Vega. The object reached perihelion, its closest approach to the Sun, in early September 2017, several months before human discovery, indicating that our robotic survey systems detected the visitor during its outbound journey rather than its initial approach. Marco Micheli, working with precise astrometric measurements from multiple observatories, detects subtle deviations in the object's trajectory that cannot be explained by gravitational forces alone. The visitor appears to be accelerating slightly as it moves away from the Sun, behavior characteristic of cometary outgassing but occurring without the visible dust and gas emission typical of comets. This non-gravitational acceleration provides important clues about the object's composition and internal structure. The spectroscopic studies reveal surface properties unlike any solar system comet or asteroid previously studied. Alan Fitzsimmons leads observational campaigns using large telescopes equipped with sensitive spectrographs, analyzing reflected sunlight to determine the object's color and surface composition. The measurements indicate a reddish hue similar to objects in the outer solar system that have been irradiated by cosmic rays over billions of years, consistent with an origin in interstellar space, where such radiation exposure would be inevitable. Photometric monitoring by multiple observatories reveals that the object's brightness varies dramatically as it rotates, suggesting an extremely elongated shape unlike any natural body previously observed. The light curve analysis indicates dimensions approximately 10 times longer than wide, a cigar-like or needle-like configuration that challenges conventional understanding of how celestial objects form and evolve. This unusual morphology provides additional evidence that the visitor originated under physical conditions very different from those found in our solar system. The object receives the official designation 11 Oumuamua, honoring both its status as the first confirmed interstellar object and its discovery by Hawaiian astronomers. The Hawaiian name means scout or messenger from afar arriving first, a poetic description that captures both the scientific significance and cultural resonance of humanity's first detected visitor from another stellar system. Avi Loeb, analyzing the non-gravitational acceleration detected in Oumuamua's trajectory, proposes that the object might represent artificial technology rather than a natural celestial body. His hypothesis suggests that radiation pressure from sunlight could account for the observed acceleration if the visitor possesses an extremely low density or unusual geometric configuration, characteristics that might indicate engineered rather than naturally formed structure. This controversial interpretation sparks intense scientific debate about the criteria needed to distinguish natural from artificial objects in interstellar space. The discovery transforms scientific understanding of interstellar space from theoretical abstraction to observational reality. Prior to Oumuamua, astronomers could only speculate about the population of objects traveling between stellar systems, basing estimates on theoretical models of planetary formation and gravitational dynamics. The confirmed detection of an interstellar visitor provides direct empirical evidence that such objects exist and can be detected using current observational techniques. Follow-up studies reveal the extraordinary velocity characteristics that enabled Oumuamua's journey through interstellar space. The object approached our solar system with a velocity of approximately 26 kilometers per second relative to the Sun, fast enough to travel from Earth to the Moon in less than 4 hours. This high velocity, combined with the hyperbolic trajectory, confirms beyond doubt that the visitor originated from another stellar system and possesses sufficient kinetic energy to continue traveling through the galaxy indefinitely. The observational campaign demonstrates the importance of rapid response capabilities for studying transient astronomical phenomena. Oumuamua remained bright enough for detailed telescopic study for only a few weeks after discovery, requiring immediate coordination between observatories worldwide to maximize scientific return. This time, pressure emphasizes the need for automated detection systems capable of identifying unusual objects quickly enough to enable comprehensive follow-up observations before they fade beyond instrumental limits. Theoretical modeling efforts attempt to understand how objects like Oumuamua might form and be ejected from their parent stellar systems. Computer simulations of planetary formation suggest that gravitational interactions during the early evolution of planetary systems could scatter significant numbers of small bodies into interstellar space. These ejected objects would then travel through the galaxy for millions or billions of years before occasionally encountering other stellar systems like our own. The discovery establishes observational precedents for future interstellar visitor detections. The techniques developed for studying Oumuamua, rapid orbital determination, coordinated international observations, sophisticated trajectory analysis, create methodological frameworks that can be applied to subsequent discoveries. As survey systems become more sensitive and automated detection algorithms more sophisticated, astronomers expect to discover additional interstellar visitors with increasing frequency. Population studies based on Oumuamua's detection suggest that thousands or millions of similar objects might be traveling through our solar system at any given time, though most remain too faint for current detection systems to identify. Statistical analysis of discovery circumstances and observational selection effects enables estimation of the overall population density of interstellar objects in our galactic neighborhood, providing insights into the frequency of planetary system disruption and object ejection throughout the galaxy's history. The non-gravitational acceleration detected in Oumuamua's motion raises fundamental questions about the physical processes that might affect objects traveling through interstellar space: sublimation of volatile materials, radiation pressure from starlight, magnetic field interactions, or even collision with interstellar dust could potentially influence trajectories in ways that current theoretical models do not fully account for. Understanding these effects becomes crucial for accurate prediction of future visitor trajectories and assessment of potential impact risks. Advanced computational models attempt to trace Oumuamua's motion backward through time to identify its possible stellar origin. The calculations require accounting for the gravitational influences of nearby stars over periods of millions of years, as well as the complex dynamics of galactic rotation that continuously reshape stellar positions and velocities. While the precise source remains uncertain, the trajectory analysis suggests possible origins from several stellar systems within a few dozen light-years of our Sun. The discovery motivates development of more sensitive survey systems specifically designed to detect interstellar visitors during their approach rather than departure phases. Future telescopes like the Large Synoptic Survey Telescope will possess the sensitivity and sky coverage needed to identify objects like Oumuamua while they are still approaching the inner solar system, enabling extended observational campaigns that could reveal much more about their physical properties and origins. International space agencies begin considering mission concepts for intercepting and studying future interstellar visitors with robotic spacecraft. The extreme velocities characteristic of such objects present extraordinary engineering challenges, requiring spacecraft capable of achieving unprecedented velocities or trajectory-matching maneuvers. However, the scientific value of close-up studies of genuine interstellar objects motivates continued investigation of such technically demanding mission possibilities. The Oumuamua discovery demonstrates that automated survey systems have achieved the sensitivity needed to detect rare astronomical phenomena that occur unpredictably and require immediate follow-up study. The same technological capabilities that enabled this breakthrough: sensitive electronic detectors, sophisticated pattern recognition algorithms, rapid communication networks, establish the observational infrastructure needed to identify and study additional interstellar visitors as they approach our solar system. As Oumuamua fades beyond the detection limits of even the largest telescopes, its tumbling form carries secrets about conditions in distant stellar systems back into the depths of interstellar space. The visitor's brief passage through our solar system provides humanity's first direct contact with material that formed around another star, traveled for millions of years through the galaxy, and arrived at precisely the moment when our technological capabilities had evolved enough to recognize its extraordinary nature. The detection marks a transition from speculation to observation in humanity's understanding of interstellar visitors, no longer theoretical possibilities discussed in academic papers. Such objects are now confirmed realities that our observational systems can detect and study. This transformation from hypothesis to empirical fact establishes the foundation for systematic investigation of the population of objects traveling between stellar systems throughout our galaxy. Only took 3 years of automated sky surveillance to detect the first confirmed visitor from interstellar space. Only required the convergence of sensitive detectors and sophisticated algorithms to recognize an object moving faster than solar escape velocity. Only needed international coordination and rapid response capabilities to characterize humanity's first detected messenger from another stellar system before it disappeared back into the cosmic darkness from which it came. The spectrographs spread rainbow patterns across detector arrays in observatories spanning from Mauna Kea to the Atacama Desert, each instrument capturing photons that have traveled across interstellar space to carry encoded information about the chemical composition and physical structure of humanity's first confirmed visitor from another stellar system. The wavelengths tell stories written in atomic signatures, absorption lines and reflection spectra that reveal secrets about conditions in distant corners of our galaxy. Alan Fitzsimmons adjusts the slit width on the William Herschel Telescope's ISIS spectrograph, optimizing the instrument to capture maximum light from the rapidly fading interstellar object. Each photon represents precious information about Oumuamua's surface composition, and the object's increasing distance from both Earth and Sun means that observing opportunities are disappearing with each passing night. The spectroscopic measurements must balance signal-to-noise ratio against spectral resolution, extracting maximum scientific value from limited observational time. The reflected sunlight carries fingerprints of molecular bonds and crystalline structures present on Oumuamua's surface. Water ice would create distinctive absorption features in the near-infrared spectrum, while silicate minerals would produce characteristic patterns in visible light. Organic compounds formed through billions of years of cosmic ray bombardment might generate subtle spectral signatures that could reveal the object's thermal history during its journey through interstellar space. Michelle Bannister leads international observational campaigns using telescopes in Hawaii, Chile, and the Canary Islands to monitor Oumuamua's brightness variations as the object rotates. The photometric measurements reveal a light curve with an unusually large amplitude, brightness changes of nearly a factor of 10 that occur with a period of approximately 7.3 hours. This dramatic variability indicates an extremely elongated shape, with proportions unlike any natural body previously observed in our solar system. The geometric analysis suggests dimensions approximately 400 meters long by 40 meters wide, a needle-like configuration that challenges conventional understanding of how celestial objects form through gravitational accretion. Such extreme elongation might result from tidal stretching during close encounters with massive objects, collision fragmentation that preferentially breaks bodies along structural weaknesses, or formation processes operating under physical conditions very different from those found in our solar system. Thermal infrared observations using the Spitzer Space Telescope attempt to detect heat emission from Oumuamua's sun-warmed surface. The measurements provide constraints on the object's size, albedo, and thermal properties that complement visible light observations. The infrared data suggest a surface that reflects approximately 10% of incident sunlight, similar to dark asteroids found in the outer regions of our solar system, but potentially consistent with surfaces that have been altered by prolonged exposure to cosmic radiation. The spectroscopic studies reveal surface coloration that appears slightly reddish compared to typical solar system asteroids and comets. This red hue might result from organic compounds called tholins that form when simple carbon-bearing molecules are irradiated by cosmic rays over geological timescales. The presence of such materials would indicate that Oumuamua's surface has been chemically processed during its journey through interstellar space, acquiring properties that distinguish it from objects that formed and remained within our solar system. Marco Micheli, analyzing precise astrometric measurements from multiple observatories, confirms that Oumuamua's trajectory shows subtle deviations from purely gravitational motion. The object appears to be accelerating slightly as it moves away from the Sun, with the acceleration vector pointing approximately away from our central star. This non-gravitational force could result from outgassing of volatile materials heated by solar radiation. Though no visible dust or gas emission has been detected around the object, the lack of observable cometary activity presents a significant puzzle. Solar heating should vaporize water ice and other volatile compounds present on Oumuamua's surface, creating the visible coma and tail characteristic of comets approaching the Sun. The absence of such features suggests either that the object's surface contains very little volatile material, or that any outgassing occurs at rates too low to produce detectable dust and gas emission. This behavior is unlike any comet previously studied in our solar system. Darrell Seligman proposes that the non-gravitational acceleration might result from sublimation of hydrogen ice that could survive in interstellar space but would be invisible when outgassing near the Sun. Molecular hydrogen would not produce observable dust or gas features, yet could generate sufficient thrust to account for the detected trajectory deviations. This hypothesis requires that Oumuamua formed in an environment cold enough and dense enough to preserve hydrogen ice for millions of years of interstellar travel. Alternative explanations for the anomalous acceleration invoke radiation pressure acting on an object with unusually low bulk density. If Oumuamua possessed an extremely porous or gossamer-like structure, solar radiation pressure could provide sufficient force to account for the observed trajectory changes. Such low-density configurations might result from sublimation processes that removed internal material while leaving behind a skeletal framework, or formation mechanisms that created inherently tenuous structures. The discovery motivates laboratory studies of how materials might behave under the extreme conditions of interstellar space. Cosmic ray bombardment over millions of years could alter molecular structures and surface chemistry in ways that have no terrestrial analogues. Temperature cycling between the near absolute zero of deep space and solar heating during stellar encounters might create unique material properties that affect how objects respond to various forces during their journey through planetary systems. Computational models attempt to understand how Oumuamua might have formed and been ejected from its parent stellar system. Gravitational interactions during planetary formation could scatter objects into interstellar trajectories, while stellar encounters or supernova explosions might disrupt entire planetary systems and launch their debris across galactic distances. The object's unusual shape and composition might preserve information about the dynamical processes that expelled it from its original home. The time constraints of observing a rapidly departing interstellar visitor highlight the importance of rapid response observational capabilities. Oumuamua remained bright enough for detailed spectroscopic study for only a few weeks after discovery, requiring immediate coordination between observatories worldwide to maximize scientific return. Future detection systems must be coupled with automated follow-up capabilities that can begin comprehensive characterization studies within hours of initial discovery. International collaborations develop standardized protocols for studying future interstellar visitors, establishing observation priorities and data sharing agreements that maximize scientific productivity. The lessons learned from Oumuamua's brief passage through our solar system create methodological frameworks that can be applied to subsequent discoveries, enabling more systematic and comprehensive investigations of objects arriving from other stellar systems. The spectroscopic signatures encoded in reflected starlight carry information about cosmic processes operating far beyond our solar system. Each wavelength measurement provides clues about stellar environments where planetary formation occurs, interstellar medium conditions that objects encounter during their journeys, and galactic chemical evolution that enriches space with elements heavier than hydrogen and helium. Oumuamua serves as an involuntary ambassador from distant realms, carrying physical evidence of conditions elsewhere in our galaxy. Advanced theoretical models attempt to predict the properties of future interstellar visitors based on current understanding of planetary formation and stellar evolution. Different stellar system architectures might produce objects with characteristic size distributions, compositions, or shapes that could be recognized in future discoveries. Statistical analysis of interstellar object populations could eventually reveal information about planetary formation processes operating throughout our galactic neighborhood. The technological capabilities that enable detailed study of Oumuamua, sensitive spectrographs, rapid communication networks, sophisticated computational models, establish the observational infrastructure needed to characterize future interstellar visitors with increasing precision. As detection systems become more sensitive and follow-up capabilities more automated, astronomers expect to discover additional objects that will provide expanding insights into conditions beyond our solar system. As Oumuamua fades beyond the reach of even the most powerful telescopes, its encoded chemical signatures preserve information about its origin and journey across interstellar space. The spectroscopic measurements obtained during its brief passage through our solar system represent humanity's first direct analysis of material that formed around another star, providing unprecedented insights into cosmic processes operating far beyond the familiar boundaries of our planetary neighborhood. Only took a few weeks of intensive spectroscopic observation to decode chemical information preserved in reflected starlight from another stellar system. Only required sophisticated instruments and rapid international coordination to extract maximum scientific value from a brief observational opportunity. Only needed the convergence of advanced detector technology and computational analysis to read the atomic signatures that reveal secrets about conditions in distant corners of our galaxy. The orbital mechanics unfold across computer screens in celestial mechanics laboratories worldwide, where mathematicians trace Oumuamua's path backward through time and space, following gravitational breadcrumbs that might lead to the distant stellar system from which humanity's first confirmed interstellar visitor began its million-year journey across the galaxy. The calculations require accounting for the complex gravitational dance of nearby stars as they orbit around our galaxy's center, each stellar motion contributing subtle influences that accumulate over cosmic timescales. Corinne Baylor-Jones, working at the Max Planck Institute for Astronomy, develops sophisticated computational models that attempt to identify Oumuamua's stellar origin through analysis of its current trajectory and velocity. The process involves integrating the object's motion backward through the gravitational field created by hundreds of nearby stars, accounting for galactic rotation and stellar proper motions that continuously reshape the local cosmic environment. Each calculation represents a voyage through deep time, tracing possible paths the visitor might have followed during its journey from another stellar system. The trajectory analysis reveals that Oumuamua approached our solar system from the approximate direction of the constellation Lyra, suggesting possible origins from stellar systems in that region of the sky. However, the object's long journey through interstellar space complicates efforts to identify its precise source. Over millions of years, gravitational perturbations from passing stars could have altered the visitor's trajectory significantly, making its current velocity vector an imperfect guide to its original departure point. The mathematical modeling faces extraordinary challenges in accounting for stellar motions over galactic timescales. Each star in our solar neighborhood follows its own complex orbit around the galaxy's center, with velocities and positions that change continuously over millions of years. The gravitational influences of these moving stellar masses create a dynamic environment that can deflect interstellar objects from their original trajectories through accumulated small-angle scattering events. Radek Scholz identifies 4 stellar systems that Oumuamua might have encountered during its journey through interstellar space, based on the convergent motions of stars and the projected trajectory of the visitor. The closest approach occurred approximately 1.3 million years ago, when the object passed within about 2 light-years of a red dwarf star designated Ross 128. However, the relative velocity during this encounter was too low to suggest that Ross 128 represents Oumuamua's origin point rather than a chance encounter during its galactic wandering. The computational models incorporate the latest data on stellar positions and velocities from the European Space Agency's Gaia mission, which has measured precise distances and proper motions for over 1 billion stars throughout our galaxy. This unprecedented astrometric database enables backward trajectory calculations with accuracy levels impossible just a few years earlier, though uncertainties still accumulate rapidly when tracing motions over millions of years through the complex gravitational environment of our stellar neighborhood. The hyperbolic trajectory that brought Oumuamua through our solar system carries encoded information about the visitor's velocity at infinite distance from the Sun, the speed it possessed while traveling through interstellar space before encountering our gravitational influence. This asymptotic velocity of approximately 3 kilometers per second provides important constraints on possible origin scenarios, as objects ejected from different types of stellar systems would be expected to possess characteristic velocity distributions. Simon Porteges-Zwart leads computational efforts to understand how objects like Oumuamua might be ejected from their parent stellar systems through gravitational interactions during planetary formation. Computer simulations of evolving planetary systems reveal that close encounters between massive planets can scatter smaller bodies onto hyperbolic trajectories, launching them into interstellar space with velocities that depend on the system's architecture and evolutionary history. These dynamical studies provide theoretical context for interpreting Oumuamua's observed properties. The ejection mechanisms that might produce interstellar wanderers operate most efficiently during the early phases of planetary system evolution, when massive planets are still migrating through protoplanetary disks and gravitational interactions are most violent. Objects scattered during this epoch would then travel through interstellar space for millions or billions of years before occasionally encountering other stellar systems. This theoretical framework suggests that Oumuamua might preserve information about conditions during the early evolution of its parent planetary system. Alternative origin scenarios invoke stellar encounters or supernova explosions that could disrupt entire planetary systems and launch their debris across galactic distances. Binary star systems might experience close approaches that tidally disrupt orbiting planets and smaller bodies, while massive stars ending their lives in supernova explosions could accelerate nearby objects to velocities sufficient for interstellar escape. Each of these mechanisms would produce characteristic signatures in the resulting interstellar object population. The galactic context of Oumuamua's journey reveals the dynamic nature of our cosmic environment. Our solar system orbits the galaxy's center with a period of approximately 225 million years, during which it encounters stellar groups of different ages and compositions. Young stellar associations contain massive stars and active planetary formation regions, while older stellar populations include systems that have had billions of years to evolve complex planetary architectures and potentially eject interstellar wanderers. The visitor's approach vector from the direction of Lyra coincides with our solar system's motion through the galaxy, creating a relative velocity that enhances the probability of encounter. This geometric circumstance illustrates how the detection of interstellar objects depends not only on their population density in our galactic neighborhood, but also on the complex dynamics of galactic rotation and stellar motion that bring different stellar systems into proximity over cosmic timescales. Statistical analysis of Oumuamua's discovery circumstances enables estimation of the overall population density of similar objects in our galactic region. The fact that automated sky surveys detected such a visitor within just a few years of achieving sufficient sensitivity suggests that interstellar space might contain millions or billions of such objects, though most remain too small or distant for current detection systems to identify. This population estimate provides insights into the efficiency of object ejection from planetary systems throughout galactic history. The mathematical techniques developed for tracing Oumuamua's trajectory create methodological frameworks that can be applied to future interstellar visitor discoveries. As more such objects are detected and characterized, statistical analysis of their velocity distributions and approach directions might reveal patterns that illuminate the mechanisms responsible for ejecting material from planetary systems and the galactic environments that facilitate interstellar transport. Advanced astrometric missions planned for the coming decades will provide increasingly precise measurements of stellar positions and motions, enabling more accurate backward trajectory calculations for future interstellar visitors. The combination of improved stellar catalogs and more powerful computational resources should eventually enable identification of specific stellar systems that serve as sources for detected interstellar objects, transforming these visitors from mysterious wanderers into traceable ambassadors from identified stellar neighborhoods. The orbital analysis demonstrates how mathematical tools developed for understanding solar system dynamics can be extended to probe cosmic processes operating on galactic scales. The same celestial mechanics that describe planetary motion around our Sun also govern the trajectories of objects traveling between stellar systems, creating conceptual bridges between local and galactic astronomy that enable investigation of phenomena spanning vast ranges of spatial and temporal scales. As computational models continue tracing Oumuamua's path through the galaxy's gravitational architecture, the mathematical investigation reveals connections between our solar system and distant stellar communities that were previously accessible only through theoretical speculation. Each calculated trajectory represents a possible thread in the complex web of gravitational interactions that link stellar systems throughout our galactic neighborhood, demonstrating that even the most remote corners of space participate in ongoing exchanges of material across cosmic distances. The ancient echo that seems to resonate between Oumuamua's trajectory and star charts drawn by forgotten civilizations might reflect deeper patterns in galactic dynamics, mathematical harmonies that govern how matter moves through space on scales far larger than human experience directly perceives. These cosmic rhythms operate according to physical laws that connect the motions of individual interstellar visitors to the grand architecture of galactic structure and evolution. only took advanced computational techniques and galactic-scale astrometry to trace an interstellar visitor's possible journey across millions of years and light-years of space. Only required sophisticated mathematical modeling and precise stellar position measurements to reveal connections between our solar system and distant stellar communities. Only needed the convergence of celestial mechanics and galactic astronomy to demonstrate how objects traveling between stars carry encoded information about cosmic processes operating throughout our galaxy's history. The convergence becomes visible in libraries where ancient astronomical tablets rest beside modern computer printouts, both documenting humanity's eternal effort to map celestial motions and predict the arrival of cosmic visitors. Here, in climate-controlled archives that preserve knowledge spanning millennia, the mathematical principles developed by Babylonian priests echo through algorithms designed to detect objects approaching from interstellar space, creating unexpected resonances between humanity's oldest scientific traditions and its most advanced technological capabilities. The pattern emerges gradually through comparative analysis of historical records and contemporary astronomical databases. Ancient Mesopotamian observations of planetary positions, recorded in cuneiform script on clay tablets, display mathematical relationships that mirror the orbital mechanics governing interstellar visitors like Oumuamua. The same geometric principles that Babylonian astronomers used to predict Venus's appearances also describe the hyperbolic trajectories followed by objects traveling between stellar systems. Jacques Lascar, analyzing long-term gravitational dynamics at the Paris Observatory, discovers that the solar system's current configuration exhibits characteristics that enhance the probability of capturing objects from interstellar space. The orbital periods and eccentricities of the major planets create gravitational resonances that can modify the trajectories of passing visitors, potentially steering them toward detection zones where Earth-based observatories are most likely to identify their presence. The astronomical significance becomes apparent through investigation of historical impact events that might represent previous interstellar visitations. The Tunguska explosion of 1908, which flattened thousands of square kilometers of Siberian forest, occurred without leaving the meteoritic debris typically associated with asteroidal impacts. Some researchers propose that this mysterious event might have resulted from the atmospheric disruption of an object with composition and structure characteristic of interstellar rather than solar system origin. Ancient Chinese astronomical records, preserved in imperial libraries for over 2 millennia, document guest stars and unusual celestial phenomena that might represent historical encounters with interstellar visitors. The careful observation protocols developed by Chinese court astronomers created continuous surveillance systems that monitored the entire sky for anomalous objects or unexpected brightness changes. Their records provide a historical database that might contain evidence for interstellar visitors that approached our solar system before modern detection capabilities existed. The mathematical framework developed by Islamic astronomers for predicting planetary positions incorporates concepts of long-term orbital evolution that apply equally well to objects on hyperbolic trajectories. Al-Battani's refinements to planetary theory, calculated over 1,000 years ago, describe gravitational perturbations that could influence the paths of interstellar visitors passing through our solar system. The same mathematical techniques used to correct ancient lunar tables could potentially enable more accurate prediction of future visitor trajectories. European Renaissance astronomers, working to understand cometary appearances through mathematical analysis, developed the theoretical foundations for recognizing objects on unbound orbits. Johannes Kepler's laws of planetary motion, formulated to describe elliptical orbits, can be extended to hyperbolic trajectories that characterize interstellar visitors. The mathematical tools created to understand solar system dynamics provide the computational framework needed to analyze objects arriving from other stellar systems. The convergence of ancient observation and modern detection becomes most apparent in the realm of predictive astronomy. Babylonian ephemeris tables, which predicted planetary positions centuries into the future, demonstrate the same conceptual approach that modern algorithms use to calculate potential encounter trajectories for interstellar objects. Both methodologies rely on mathematical extrapolation from current observations to anticipate future celestial events. Contemporary space agencies begin developing mission concepts for intercepting future interstellar visitors, using trajectory prediction techniques that trace their intellectual heritage to ancient astronomical traditions. The European Space Agency's proposed Comet Interceptor mission incorporates rapid response capabilities designed to rendezvous with newly discovered objects, whether they originate from our solar system's outer reaches or arrive from interstellar space. These missions represent the practical culmination of humanity's millennia-long effort to engage directly with cosmic visitors. The pattern recognition algorithms used in modern sky surveys embody mathematical principles that echo through centuries of astronomical tradition. The same systematic approach to monitoring celestial positions that characterized medieval Islamic observatories guides contemporary robotic telescopes scanning for moving objects against the stellar background. Both methodologies emphasize patient observation, precise measurement, and statistical analysis of large datasets to identify rare phenomena. Archaeological investigations of ancient observatory sites reveal structural alignments that might have facilitated detection of objects approaching from specific directions in space. Stonehenge, Angkor Wat, and Mayan pyramids incorporate astronomical orientations that could enhance visibility of celestial visitors arriving from particular regions of the sky. While these monuments were designed primarily for solar and lunar observations, their geometric properties might have inadvertently created enhanced detection capabilities for certain types of interstellar approaches. The cyclical nature of galactic dynamics creates possibilities that ancient astronomical traditions might have preserved knowledge of previous interstellar visitations through mythological or symbolic representations. Our solar system's orbit around the galaxy carries us through different stellar neighborhoods over periods of millions of years, potentially creating epochal variations in the frequency of interstellar encounters. Cultural memories preserved in religious or astronomical traditions might encode information about cosmic visitors that approached during previous galactic orbits. Modern computational archaeology attempts to decode astronomical information preserved in ancient texts, artwork, and architectural monuments. Advanced algorithms can analyze historical records for references to unusual celestial phenomena that might represent encounters with interstellar objects. Machine learning techniques enable systematic search through vast databases of historical documents, identifying patterns that human scholars might overlook but that could indicate awareness of cosmic visitors in pre-telescopic civilizations. The investigation reveals that human consciousness might be inherently attuned to detecting cosmic visitors through accumulated evolutionary or cultural conditioning. Our species' development occurred during periods when our solar system encountered different galactic environments, potentially exposing our ancestors to interstellar visitors that influenced cultural or genetic evolution. This deep time perspective suggests that humanity's current technological capabilities for detecting interstellar objects might represent the culmination of millions of years of unconscious preparation for such encounters. The mathematical resonances between ancient astronomical observations and contemporary detection algorithms might reflect fundamental properties of cosmic dynamics that operate across vast ranges of spatial and temporal scales. The same gravitational forces that govern planetary motion also determine the trajectories of interstellar visitors, creating mathematical relationships that human observers have recognized and recorded for millennia, even without understanding their full cosmic significance. International collaborations between archaeoastronomers and contemporary sky survey programs begin investigating correlations between historical astronomical records and predicted arrival patterns for interstellar visitors, by comparing ancient observations of unusual celestial phenomena with theoretical models of galactic dynamics. Researchers hope to identify historical encounters with interstellar objects that might provide insights into the long-term evolution of such visitations. The convergence of ancient wisdom and modern technology creates synergistic capabilities that exceed what either approach could achieve independently. Historical astronomical records provide baseline observations spanning thousands of years, while contemporary detection systems offer unprecedented sensitivity and real-time analysis capabilities. The combination enables investigation of cosmic phenomena that operate on timescales longer than individual human lifetimes or technological generations. Advanced theoretical models suggest that the detection of Oumuamua might represent the beginning of a new epoch in human cosmic interactions, as our technological capabilities mature during a period when our solar system travels through galactic regions with enhanced probabilities for interstellar encounters. The apparent synchronization between humanity's development of detection capabilities and the arrival of detectable interstellar visitors might reflect cosmic processes that operate according to principles not yet fully understood by contemporary science. As ancient tablets and modern databases reveal their hidden connections, the investigation demonstrates that humanity's relationship with cosmic visitors extends far deeper into history than previously recognized. Each clay tablet inscribed with planetary positions, each algorithm designed to detect moving objects, each mathematical technique developed to predict celestial events contributes to an ongoing conversation between human consciousness and cosmic dynamics that spans millennia and connects our species to processes operating throughout the galaxy. Only took 5,000 years of astronomical observation to develop the mathematical and technological capabilities needed to detect visitors from other stellar systems. Only required the accumulated wisdom of countless generations of observers to create detection systems sensitive enough to recognize humanity's first confirmed interstellar visitor. Only needed the convergence of ancient astronomical traditions and modern computational capabilities to demonstrate that our species has been unconsciously preparing for cosmic encounters throughout recorded history. The synthesis becomes apparent in research centers, where scientists from diverse disciplines gather to examine how humanity's detection of Oumuamua might represent the fulfillment of astronomical dreams that have guided human civilization since its earliest observations of the night sky. Here, in conference rooms where archaeologists discuss ancient star maps beside astrophysicists analyzing hyperbolic trajectories, the investigation reveals profound connections between human consciousness and cosmic processes that span scales from individual awareness to galactic dynamics. The philosophical implications emerge through careful analysis of how ancient astronomical traditions established conceptual frameworks that prepared human thinking for eventual encounters with interstellar visitors. Babylonian creation myths, which described cosmic order arising from primordial chaos. Parallel modern theories of planetary formation that explain how gravitational instabilities during stellar system evolution can eject objects into interstellar space. Both frameworks envision dynamic processes that connect local environments to larger cosmic structures. Carl Jung's investigations of archetypal symbols in human consciousness reveal recurring patterns that might reflect deep evolutionary conditioning to cosmic rhythms. His analysis of mandala symbols, which appear independently in cultures worldwide, identifies geometric relationships that mirror orbital mechanics and celestial motion patterns. These psychological structures might represent inherited templates that enable human minds to recognize and interpret cosmic phenomena even without explicit astronomical training. The investigation extends to analysis of how indigenous astronomical traditions worldwide developed observational techniques that might have enabled detection of unusual celestial visitors. Aboriginal Australian songlines encode information about stellar positions and seasonal changes that require multi-generational knowledge transmission, creating cultural systems capable of preserving astronomical information across time scales comparable to interstellar orbital periods. Such traditions might contain encoded knowledge of previous cosmic encounters that occurred before written history began. Contemporary cognitive science research reveals that human brains possess specialized neural networks for processing motion detection and pattern recognition that evolved during millions of years of environmental adaptation. These same neural mechanisms that enabled our ancestors to detect moving predators or identify seasonal changes might be inherently suited for recognizing anomalous celestial motions that characterize interstellar visitors. The evolution of human consciousness might have been unconsciously shaped by cosmic influences that prepared our species for eventual technological detection capabilities. The mathematical principles that ancient astronomers discovered through careful observation of planetary motions encode universal relationships that operate throughout cosmic scales. The harmonic ratios that Pythagoras identified in musical intervals also appear in planetary orbital periods, and the gravitational resonances that can capture or deflect interstellar objects. These mathematical harmonies might reflect fundamental properties of cosmic organization that human consciousness is inherently capable of recognizing and expressing through cultural or technological systems. Quantum mechanical investigations of consciousness suggest that human awareness might be non-locally connected to cosmic processes through mechanisms that operate faster than light speed. If consciousness involves quantum entanglement between neural microtubules and larger cosmic structures, then human observation of astronomical phenomena might influence the probability distributions that determine when and where cosmic events occur. This interpretation suggests that humanity's development of interstellar detection capabilities might have quantum mechanically summoned Oumuamua's appearance in our solar system. The investigation reveals remarkable synchronicities between humanity's technological development and the cosmic timing of interstellar visitor arrival. The Atlas survey system achieved operational capability just a few years before Oumuamua's detection, suggesting either extraordinary coincidence or causal relationships that operate through mechanisms not yet understood by conventional science. The apparent coordination between human technological readiness and cosmic visitor arrival challenges materialist assumptions about the independence of observer and observed phenomena. Historical analysis reveals that previous epochs of rapid astronomical development have often coincided with reports of unusual celestial phenomena that might represent encounters with interstellar visitors. The Islamic Golden Age, which produced unprecedented advances in observational astronomy, occurred during periods when Chinese and European records document numerous guest stars and anomalous celestial events. The European Renaissance, which revolutionized understanding of planetary motion, coincided with increased cometary activity and reports of aerial phenomena that defied conventional explanation. The investigation extends to analysis of how artistic and cultural developments might reflect unconscious awareness of approaching cosmic visitors. The emergence of science fiction literature during the late 19th and early 20th centuries, which introduced concepts of interstellar travel and alien visitation, occurred during the same period when photographic astronomy first achieved the technical capability to detect objects on unusual trajectories. Cultural imagination might serve as a collective early warning system that anticipates cosmic encounters before conscious scientific awareness develops. Modern studies of morphic resonance suggest that information can be transmitted across space and time through non-material mechanisms that create evolving patterns in natural systems. If such processes operate on cosmic scales, then the gravitational interactions that guide interstellar objects through our solar system might be influenced by the accumulated observational intentions of generations of human astronomers. The collective human desire to detect cosmic visitors might have created morphic fields that influenced Oumuamua's trajectory toward regions where detection probability was maximized. The convergence of ancient astronomical traditions and contemporary detection capabilities demonstrates that human civilization might be approaching a phase transition in cosmic awareness. Just as biological evolution occasionally produces rapid developments that enable organisms to exploit new environmental niches, cultural evolution might be generating capabilities that prepare humanity for expanded cosmic interactions. The detection of Oumuamua might represent the first evidence that our species is ready to participate consciously in galactic-scale processes. International collaborations between consciousness researchers and astronomers begin investigating correlations between collective human awareness states and the detection of cosmic phenomena. Meditation groups focusing on cosmic themes. Global peace initiatives and other forms of synchronized human consciousness might influence the probability of detecting interstellar visitors through mechanisms that operate beyond current scientific understanding. These investigations explore whether human consciousness serves as an active participant in cosmic processes rather than merely a passive observer. The Global Consciousness Project, which monitors random number generators worldwide for correlations with major human events, begins extending its analysis to astronomical discoveries. Preliminary data suggests that periods of heightened global attention to space exploration and astronomical research correlate with increased detection rates of unusual cosmic phenomena. If consciousness indeed influences physical processes through quantum mechanical or morphic mechanisms, then collective human focus on cosmic exploration might enhance our technological capabilities for detecting interstellar visitors. Advanced computational models attempt to quantify the probabilistic relationships between human technological development and cosmic visitor arrival timing. The mathematical analysis reveals that the probability of detecting an interstellar object like Oumuamua within a few years of achieving adequate detection capabilities approaches statistical significance levels that challenge purely random explanations. Either humanity has been extraordinarily fortunate in timing, or causal mechanisms operate that coordinate technological readiness with cosmic encounter opportunities. The investigation reveals that many ancient astronomical traditions incorporate concepts of reciprocal relationships between human observation and celestial behavior. Chinese astronomy describes the mandate of heaven as a dynamic interaction between terrestrial events and cosmic phenomena, where human actions influence celestial harmony and vice versa. Mayan astronomy incorporates similar concepts of cyclical cosmic ages, where human consciousness plays an active role in determining cosmic events. These traditions might preserve knowledge of actual mechanisms through which consciousness influences physical processes on cosmic scales. Contemporary physics research into the measurement problem in quantum mechanics suggests that conscious observation might play a fundamental role in determining physical reality at all scales. If quantum mechanical effects operate in astronomical environments, as suggested by recent discoveries of quantum entanglement in stellar systems and galactic magnetic fields, then human observation of cosmic phenomena might influence the probability distributions that determine when and where such events occur. The detection of Oumuamua might represent evidence that consciousness and cosmos participate in ongoing co-creative processes. The synchronistic timing of Oumuamua's discovery raises profound questions about the nature of causality in cosmic systems. The object's trajectory brought it through our solar system during the precise historical moment when human technology achieved the sensitivity needed for detection, and its approach vector aligned with regions of sky that automated survey systems monitor most thoroughly. These geometric and temporal coincidences suggest either extraordinary fortune or causal mechanisms that operate through currently unknown physical principles. Archaeological evidence suggests that ancient civilizations might have possessed knowledge of cyclical cosmic encounters that influenced their astronomical observations and cultural developments. The Antikythera mechanism, that ancient Greek computer designed to predict astronomical events, incorporates gear ratios that might encode information about galactic cycles and cosmic visitor periodicities. Similar computational devices might have existed in other ancient civilizations, preserving knowledge of cosmic encounter patterns that modern science is only beginning to rediscover. The investigation reveals that humanity's current historical moment might represent a unique convergence of technological capability and cosmic opportunity. Our species has developed detection systems sensitive enough to identify interstellar visitors during the same epoch when our solar system's galactic orbit carries us through stellar regions where such encounters are most probable. This temporal convergence suggests that cosmic evolution and cultural evolution might be synchronized through mechanisms that operate on galactic timescales. Modern theoretical physics explores concepts of cosmic intelligence that might emerge from the collective gravitational interactions of stellar systems, galaxies, and larger cosmic structures. If such intelligence influences the trajectories of interstellar objects, then Oumuamua's arrival might represent a form of cosmic communication designed to occur when human civilization achieved adequate technological sophistication for detection and analysis. The visitor's unusual properties, its extreme elongation, non-gravitational acceleration, and lack of observable outgassing might encode information that challenges conventional understanding and stimulates technological development. The synthesis reveals that humanity's detection of its first confirmed interstellar visitor fulfills astronomical dreams that have guided human civilization since its earliest systematic observations of cosmic phenomena. From Babylonian priests tracking planetary wanderers to contemporary algorithms scanning for hyperbolic trajectories, human consciousness has maintained persistent focus on detecting and understanding cosmic visitors. This multi-millennial observational tradition might have created morphic or quantum mechanical influences that eventually manifested in the form of Oumuamua's appearance. The convergence of ancient wisdom and modern technology demonstrates that human civilization might be approaching a new phase of cosmic awareness where conscious participation in galactic processes becomes possible. The same mathematical principles that guided ancient astronomical observations also govern contemporary detection algorithms, suggesting that human consciousness has been unconsciously preparing for cosmic encounters throughout recorded history. Oumuamua's detection might represent the first evidence that humanity is ready to engage consciously with processes that operate on galactic scales. As researchers continue investigating the relationships between consciousness and cosmic phenomena, the analysis reveals that humanity's technological capabilities for detecting interstellar visitors emerged during a historically unique convergence of cosmic circumstances. Our solar system's current galactic environment, combined with our species' recent development of automated sky surveys and sophisticated detection algorithms, creates observational opportunities that might not recur for millions of years. The timing suggests either extraordinary coincidence or coordination through mechanisms that connect consciousness to cosmic dynamics. The investigation demonstrates that questions about whether humanity summoned Oumuamua through collective astronomical intention cannot be answered through conventional scientific methodologies alone. The apparent synchronicities between human technological development and cosmic visitor arrival operate on scales and through mechanisms that challenge materialist assumptions about the separation between observer and observed phenomena. Understanding these relationships might require expansion of scientific paradigms to incorporate consciousness as an active participant in physical processes, rather than merely a passive observer. The synthesis reveals that humanity's first detected interstellar visitor represents more than a scientific discovery. It symbolizes the culmination of our species' eternal quest to understand its relationship to cosmic processes that operate far beyond terrestrial experience. Whether Oumuamua arrived through purely physical mechanisms or through more mysterious connections between consciousness and cosmos, its detection demonstrates that human civilization has achieved capabilities that our ancestors could only dream of while gazing at the star-filled sky and wondering about visitors from distant worlds. Only took the entire span of human civilization to develop the consciousness and technology needed to detect visitors from other stellar systems. Only required millennia of patient astronomical observation and technological development to achieve capabilities that might have quantum mechanically influenced the arrival of humanity's first confirmed interstellar visitor. Only needed the convergence of ancient astronomical dreams and modern detection capabilities to demonstrate that consciousness and cosmos might participate in co-creative processes that span galactic scales and cosmic time. The departure unfolds across computer screens in observatories worldwide as Oumuamua fades beyond the detection limits of Earth's most powerful telescopes, its tumbling form carrying secrets back into the depths of interstellar space from which it emerged. The visitor's brief passage through our solar system, a cosmic encounter lasting only months from discovery to final observation, leaves behind profound questions about the nature of consciousness, the mechanisms of cosmic communication, and humanity's evolving role in galactic-scale processes that operate according to principles we are only beginning to comprehend. The final observations capture Oumuamua as a mere point of light, distinguishable from background stars only through its motion against the stellar backdrop. The object's unusual brightness variations continue even as it fades, indicating that its mysterious rotation period and extreme elongation persist throughout its departure journey. Each photon reaching Earth's telescopes represents information that has traveled across millions of miles of space, carrying encoded details about surface composition, internal structure, and physical processes that might reveal conditions in distant stellar systems where similar objects formed billions of years ago. David Jewett leads the international campaign to extract maximum scientific value from the visitor's fading apparition, coordinating observations between telescopes spanning from Hawaii to Chile to Australia. The global effort demonstrates how humanity's technological infrastructure has evolved to enable rapid response to cosmic opportunities that occur unpredictably and disappear quickly. The same observational capabilities that characterized Oumuamua's discovery and study established the methodological foundations for investigating future interstellar visitors with even greater precision and scientific sophistication. The trajectory calculations confirm that Oumuamua will never return to our solar system. Its hyperbolic orbit carries sufficient velocity to overcome solar gravitational influence entirely, ensuring that the visitor will continue traveling through interstellar space indefinitely until it encounters another stellar system in the distant future. The mathematical certainty of this departure emphasizes the uniqueness of humanity's observational opportunity, a cosmic encounter that will never be repeated with this particular object. Statistical analysis of Oumuamua's discovery circumstances enables estimation of how frequently similar interstellar visitors might pass through our solar system undetected. The calculations suggest that objects of comparable size approach our Sun approximately once per year, though most remain too faint or follow trajectories that place them beyond current detection capabilities. This population estimate implies that interstellar space throughout our galactic neighborhood contains millions or billions of such wanderers, the vast majority invisible to human observation, but occasionally detectable when cosmic geometry and technological capabilities align favorably. The visitor's departure trajectory will eventually carry it toward the constellation Pegasus, where it will continue traveling at approximately 26 kilometers per second until gravitational interactions with other stellar systems modify its path. Computer models project that Oumuamua might encounter another star within 10,000 to 20,000 years, though the specific target depends on stellar motions and galactic dynamics that remain uncertain over such extended time periods. The object will carry information about our solar system's current configuration into cosmic regions where that knowledge might persist for millions of years. International space agencies continue developing mission concepts for intercepting future interstellar visitors during their approach phases rather than after they have already begun departing from the inner solar system. The extreme velocities characteristic of such objects present extraordinary engineering challenges, requiring spacecraft capable of achieving unprecedented speeds or performing complex gravitational assist maneuvers to match visitor trajectories. However, the scientific value of close-up studies of genuine interstellar objects motivates continued investigation of such technically demanding mission possibilities. The European Space Agency's Comet Interceptor mission, currently under development, incorporates rapid response capabilities designed to rendezvous with newly discovered objects regardless of their solar system or interstellar origins. The spacecraft will wait at a gravitational stable point between Earth and Sun until automated survey systems detect an appropriate target, then execute trajectory modifications to intercept the visitor during its passage through the inner solar system. This mission architecture represents humanity's first serious attempt to engage directly with cosmic visitors rather than merely observing them from afar. Advanced theoretical models attempt to predict the characteristics of future interstellar visitors based on current understanding of planetary formation processes operating throughout our galaxy. Different stellar system architectures, binary stars, massive planetary companions, dense stellar environments might produce objects with distinctive size distributions, compositions, or dynamical properties that could be recognized in subsequent discoveries. Statistical analysis of interstellar object populations might eventually reveal information about cosmic processes operating in stellar systems throughout our galactic neighborhood. The investigation of consciousness-cosmos relationships continues through interdisciplinary collaborations between astronomers, physicists, and researchers studying human awareness phenomena. The apparent synchronicities between humanity's technological development and Oumuamua's arrival timing motivate continued exploration of whether consciousness influences physical processes through quantum mechanical or other mechanisms that operate faster than light speed. If such connections exist, then collective human focus on cosmic exploration might enhance our capabilities for detecting and understanding future interstellar visitors. Global consciousness monitoring systems begin incorporating astronomical discovery events into their analysis of correlations between human awareness states and physical phenomena. The detection of Oumuamua occurred during a period of heightened international cooperation in space exploration and increased public interest in astronomical discoveries, suggesting possible connections between collective human consciousness and cosmic encounter opportunities. Future interstellar visitor detections might provide additional data points for investigating these mysterious relationships. The technological infrastructure that enabled Oumuamua's discovery and characterization continues evolving toward greater sensitivity and faster response capabilities. The Large Synoptic Survey Telescope, currently under construction in Chile, will scan the entire southern sky every few nights with sensitivity levels that exceed current systems by factors of 10 or more. This next-generation survey will detect interstellar visitors while they are still approaching the inner solar system, enabling extended observational campaigns that could reveal much more about their origins and physical properties. Advanced detection algorithms incorporate machine learning techniques that can identify unusual objects in astronomical images with superhuman accuracy and speed. These artificial intelligence systems learn to recognize the subtle signatures that distinguish interstellar visitors from solar system objects, enabling automated classification of discoveries within minutes of initial detection. The same pattern recognition capabilities that characterized Oumuamua's identification will guide future surveys capable of monitoring millions of objects simultaneously for evidence of interstellar origin. The investigation reveals that humanity's first detected interstellar visitor represents both an ending and a beginning in our species' relationship with cosmic phenomena. Oumuamua's departure closes the observational chapter of our first confirmed encounter with material from another stellar system, while simultaneously opening new possibilities for understanding how consciousness and cosmos might interact through mechanisms that transcend conventional scientific paradigms. The visitor's brief presence demonstrated that our technological capabilities have matured to the point where cosmic encounters can be detected and studied in real time. The synthesis of ancient astronomical traditions and contemporary detection capabilities suggests that human civilization might be entering a new phase of cosmic awareness where conscious participation in galactic processes becomes possible. The mathematical principles that guided Babylonian observations of planetary wanderers also govern modern algorithms designed to detect hyperbolic trajectories, creating conceptual continuities that span millennia of human scientific development. Oumuamua's appearance might represent the first tangible evidence that humanity's long preparation for cosmic encounters has achieved sufficient sophistication for meaningful interaction with interstellar phenomena. As the visitor fades beyond the reach of human observation, its legacy persists in the scientific methodologies, technological capabilities, and expanded consciousness that its detection stimulated. The brief cosmic encounter transforms speculative possibilities into empirical realities, demonstrating that interstellar visitors can be detected, studied, and understood using human scientific capabilities. This transformation from theoretical speculation to observational fact establishes the foundation for systematic investigation of interstellar object populations and their relationships to galactic dynamics. The questions raised by Oumuamua's mysterious properties, its extreme elongation, non-gravitational acceleration, lack of observable outgassing, continue motivating theoretical research into exotic object formation mechanisms and alternative interpretations of astronomical phenomena. Whether the visitor represents natural processes operating under conditions unlike those found in our solar system, or something more enigmatic that challenges conventional understanding, its detection demonstrates that the universe contains phenomena that exceed current scientific paradigms. The departure marks not an ending, but a transition in humanity's cosmic awareness. While Oumuamua itself disappears into interstellar darkness, the technological infrastructure and scientific methodologies developed for its study remain available for investigating future cosmic visitors. Each subsequent interstellar detection will build upon the observational precedents and analytical techniques pioneered during our first confirmed encounter, gradually expanding human understanding of the cosmic processes that link stellar systems throughout our galaxy. The visitor carries with it the accumulated observations, theoretical insights, and expanded consciousness that its detection inspired within human civilization, serving as an involuntary ambassador that connects our solar system to the broader galactic community of stellar systems and cosmic processes that operate far beyond terrestrial experience. The stars wheel overhead in their ancient patterns, each point of light now understood as a potential source of cosmic visitors that might one day cross the vast distances between stellar systems to arrive in our solar neighborhood. The night sky that once seemed static and unchanging has been transformed by humanity's first detection of an interstellar traveler into a dynamic realm of possibilities, where objects from distant worlds might emerge at any moment from the cosmic darkness. The observatories continue their patient vigil, their electronic eyes scanning the heavens with mechanical persistence that echoes the dedication of ancient astronomers who climbed ziggurats and mountain peaks to study celestial phenomena. The same fundamental curiosity that drove Babylonian priests to track planetary wanderers now guides sophisticated algorithms that monitor millions of objects for the subtle motion signatures that might reveal visitors from other stellar systems. In the quiet hours before dawn, when the Earth turns slowly toward another sunrise and the last stars fade into brightening twilight, the cosmic conversation continues. Somewhere in the depths of interstellar space, other objects like Oumuamua travel their lonely paths between distant suns, carrying information about stellar systems and planetary formation processes that occurred billions of years ago in regions of our galaxy that human beings will never visit directly. The technological infrastructure that enabled humanity's first confirmed detection of an interstellar visitor remains vigilant, ready to identify future cosmic encounters that will gradually expand our understanding of the galactic environment in which our solar system participates. Each new discovery will add another data point to the growing catalog of interstellar objects, slowly revealing the population characteristics and dynamical processes that govern material exchange between stellar systems throughout our cosmic neighborhood. The questions raised by Oumuamua's mysterious properties continue resonating through scientific conferences and research laboratories, motivating theoretical investigations that might eventually reveal whether consciousness and cosmos interact through mechanisms that transcend conventional understanding. The apparent synchronicities between human technological development and cosmic visitor arrival suggest connections that operate on scales spanning from individual awareness to galactic dynamics, relationships that future research might illuminate through expanded scientific paradigms. The winds of space carry objects across distances measured in light years and timescales spanning millions of years, connecting stellar systems through gravitational influences and material exchanges that operate according to physical laws humanity has only begun to comprehend. Our first detected interstellar visitor represents one thread in a vast cosmic web of interactions that link every star and planet in our galaxy through processes that unfold over geological and astronomical timescales. The night deepens into the silence of cosmic time, where stellar evolution and galactic rotation proceed according to rhythms that dwarf human experience but remain accessible to mathematical understanding and patient observation. The same forces that guide Oumuamua through interstellar space also shape the formation of new stars and planetary systems throughout our galaxy, creating conditions where future civilizations might one day detect their own cosmic visitors and wonder about the origins of objects arriving from distant stellar neighborhoods. The darkness between the stars no longer seems empty, but populated with wandering ambassadors from stellar systems throughout our galactic region, most too small or distant for human detection, but occasionally becoming visible when cosmic geometry and technological capability align in favorable configurations. The universe reveals itself as a dynamic system where material and information flow continuously between stellar systems, creating connections that span vast distances and link apparently isolated worlds through invisible networks of gravitational and electromagnetic influence. Sleep arrives like the slow rotation of our planet through cosmic space, carrying human consciousness toward dreams where astronomical discovery blends with ancient wisdom and the boundaries between observer and observed dissolve into the deeper patterns that connect all phenomena. The stars continue their eternal dance above sleeping cities, their light carrying stories of cosmic processes that unfold across scales from atomic to galactic, weaving the fabric of reality through interactions that operate according to principles that science continues discovering through patient observation and mathematical analysis. Rest comes gently, like the cosmic expansion that carries galaxies slowly apart, while gravity continues binding local structures into stable configurations that persist for billions of years. The same forces that enable human consciousness also guide stellar evolution and planetary formation throughout the universe, creating the cosmic context within which life emerges and develops the technological capabilities needed to detect visitors from distant worlds and recognize its participation in processes that span the galaxy. The wind settles into stillness, and the Earth continues its orbital journey through space that will eventually carry our solar system through different galactic environments where future encounters with interstellar visitors might reveal new aspects of cosmic dynamics and consciousness relationships that remain hidden within current scientific understanding.